Okay. All right. So very good evening all. In the yesterday's session, we discussed about the center tapped transformer configuration, that is the full wave control rectifier, okay, with R load and RL load. As I said, yes. Right. So generally, the center tapped transformer configuration is not preferred due to the more PIV rating is required. Okay, we discussed the PIV rating required is equal to 2 times the V max. Right now, center tapped transformer configuration as well as whatever the now we are going to discuss, that is the bridge type configuration. Both are the full wave rectifiers only. For R load, RL load, RL with freewheeling diode, RL E load, okay, whatever the waveforms we are going to discuss in the bridge type configuration for V0 and I0, the same waveforms will appear there for a center tapped transformer configuration also, because both are the full wave controlled rectifiers only, right? So let me put the heading: single phase full wave controlled rectifier. In that, now we are going to discuss the bridge configuration. Okay, bridge configuration. Yes. So in the bridge configuration, again there are two types. One is the fully controlled bridge configuration. Second one is the half controlled bridge configuration. In the half controlled, again we are having the two different configurations. One is the symmetrical configuration and second one is the asymmetrical configuration. Okay, so that everything we are going to discuss today. Okay, and if the time permits, we'll discuss some numericals, right? So let us first discuss the fully controlled bridge configuration. Fully controlled bridge configuration. Yes. In the fully controlled bridge configuration, we require 4 thyristors. Okay. So let us discuss for purely resistive load first with the R load. So let me draw the circuit diagram. It consists of 4 thyristors. Right? This is supply voltage Vs, which is equal to Vm into sine of omega t. Thyristors were having it is a T1, T2, T3 and T4, right? Let us consider voltage across this thyristor is a Vt1. This current is a Is. Current flowing through thyristor T1, let us consider it as a It1. R, this is a V0 and here it is a I0. Similarly, right here Vt2 and this is the I2. Okay, sorry, It2. This should be the It2. Right? In the waveforms, Vs is equal to Vm into sine of omega t. Right? Pure sinusoidal supply voltage. Pi, 2 pi, and here it is a 3 pi. This is a Vs. Next, gate pulse to thyristors. This is a alpha, pi plus alpha, and 2 pi plus alpha, right? So This is get pulse to thyristors T1 and T2. So let me write it as a Ig1, Ig2. This is the T3, T4 get pulse. That is Ig3, Ig4, and again Ig1, Ig2, and it repeats. Next one is the V0 and I0. This is a V0 and next one is the I0. You can check the V0 I0 waveform for midpoint tapped transformer configuration with a purely resistive load. The same waveform we got there also, right? So this one is a V0 and red one is a I0. And here it is a alpha pi plus alpha 2 pi plus alpha, and here it is a 3 pi, right? So here this is again a full wave controlled rectifier only, right? So full wave control rectifier means corresponding to one input cycle. In the output, yes, we'll be getting the two pulses na. So you can check corresponding to one input cycle, that is from 0 to 2 pi. In the output we are having two pulses. This is the first pulse, this is the second pulse. Okay, so if the input supply frequency is 50 hertz, output pulse frequency is equal to 100 hertz. Okay, now let us discuss the circuit operation. So Vs is Vm into sine of omega t. So from 0 to pi, Vs is positive, pi to 2 pi negative, 2 pi to 3 pi, again it is a positive, right? So when Vs is positive, consider the polarity is plus here and minus here. So when Vs is negative, definitely we need to reverse it. Okay, so if it is a plus here, here it is a minus. It is like this is the highest potential point, this is the lowest potential point in the circuit. Okay, so highest potential and the lowest potential. So you can check this highest potential is appearing here, this lowest potential is appearing here. Okay, so what it indicates, the highest potential is appearing at the anode of thyristor T1. At the same time, this highest potential is appearing at the cathode of thyristor T4. Yes or no? Right? So I'm repeating, highest potential is appearing at the anode of T1 as well as the highest potential is appearing at the cathode of T4. So now highest potential is appearing at the anode of T1, means anode of the thyristor T1 is at a highest potential. So can we say that thyristor T1 will be in a forward bias mode, right? Similarly, highest potential is appearing at the cathode of thyristor T4. So can we say that cathode is at highest potential? So definitely can we say that thyristor T4 will be in a reverse bias mode, right? So from this terminal or from this potential, we can say that T1 is a forward bias mode, T4 is in a reverse bias mode. Similarly, the lowest potential is appearing here. So the lowest potential is connected to, you can check lowest potential point is connected to the anode of thyristor T3 and cathode of thyristor T2. Okay, so anode of thyristor T3 is at a lowest potential. So anode is at lowest potential. So can we say that thyristor T3 will be in a reverse bias mode, right? Similarly, you can check the lowest potential is appearing at the cathode of T2. Okay, so can we say that cathode is at the lowest potential, means definitely thyristor T2 will be in a forward bias mode. Okay, for any thyristor, if the anode potential is highest, means it is like that thyristor will be in a forward bias mode. If the anode potential is lowest, then the thyristor will be in a reverse bias mode. If cathode potential is highest, thyristor will be in a reverse bias mode. If cathode potential is lowest, thyristor will be in a forward bias mode. Okay, so similarly we have yes, we can write here, when Vs is positive, T1 T2 will be in a forward bias mode, T3 T4 reverse bias mode. Okay, so let me write here, when Vs is positive, just a minute. Just a minute. The sketchbook is not responding. I will close it and again reshare. Okay. Yes. Please wait for some time. I don't know why I'm getting. Okay. Okay. I don't know, that file was not responding, right? So yeah, other files were responding, right? Yesterday and day before yesterday, whatever we saved that, but that file was not responding. Okay, so let us start fresh again. Okay, so yes, I hope now it is responding. Check once. Yeah, now it is fine. Yes, single phase full wave controlled rectifier, bridge configuration. In that, first we are going to discuss the full bridge configuration or fully controlled bridge configuration. Fully controlled bridge configuration, and the load is purely resistive R load, right? So let me draw the circuit diagram. So as this is a fully controlled, so we are using the 4 thyristors here. Vs, T1, T2, T3, and here it is T4. Here we are having a load branch, purely resistive load. This voltage is V0, current is I0, right? Plus minus, this is a VT1, this current is a IT1, this voltage is VT2, this current is a IT2, right? In the waveforms, yes, waveform for the supply voltage, which is equal to Vm into sine of omega t. Right? 0 to pi, pi to 2 pi, and 2 pi to 3 pi. Next, gate pulse to thyristor. Yes. At omega t is equal to alpha, we're going to apply the gate pulse to thyristor T1, T2 at pi plus alpha, T3, T4 at 2 pi plus alpha, again T1, T2, right? Okay. So this is the waveform, sorry, gate pulse to thyristors T1, T2, and the red one is the gate pulse to thyristor T3, T4. And next one will be again T1, T2. Okay, so alternately we are going to apply the gate pulse to thyristors T1, T2, and again T3, T4, right? This is a V0 and I0. Right? This is V0 and the I0. It's like alpha pi, pi plus alpha, 2 pi, 2 pi plus alpha here, and it will be 3 pi, right? So yes, so we're having a circuitry which consists of 4 thyristors T1, T2, T3, T4. As in the bridge configuration, we require 4 switches. All these 4 are the controlled switches. That's why it is a fully controlled bridge configuration. Okay. Next, let us discuss the purely resistive load. So whatever we discussed earlier, when Vs is positive, it is a plus here, minus here. So this plus will appear here, this minus will appear here. Okay. So highest potential point will appear at the anode of thyristor T1. So thyristor T1 forward bias. Highest potential will appear is appearing at the cathode of thyristor T4. So T4 will be in a reverse bias. Lowest potential is appearing at the anode of thyristor T3. So T3 will be in a reverse bias. Lowest potential is appearing at a cathode of T2. So T2 will be in a forward bias. Okay. So let me write, when Vs is positive, when Vs is positive, yes, it is like a T1, T2 are in a forward bias mode, right? And T3, T4 will be in a reverse bias mode. Reverse bias mode. Okay. So importantly, when Vs is positive, T1, T2 are in a forward bias mode. Na? So that's why you can check when Vs is positive, we are going to apply the gate pulse to only thyristors T1, T2, right? Because T3, T4 are in a reverse bias mode. Even though if we apply the gate signal, the T3, T4 will not turn on, right? So that's why only T1, T2 gate pulse were applied. Similarly, you can check if this is for Vs positive. So for Vs negative, what will happen? This will be reversed. Na? Here it is minus, here it is plus. So here it is minus, here it is plus. Okay. So it will be like lowest potential will be appearing at the cathode of T4. Highest potential will be appearing at the anode of T3. So T3, T4 forward bias, T1, T2 reverse bias, right? So simply opposite to that of this one. So when Vs is negative, yes, it is like a T1, T2 reverse bias and T3, T4 forward bias. Okay, T3, T4 forward bias. Okay, so we're having T1, T2, T3, T4. So here you can check T3, T4 and forward bias. So when Vs is negative, we're going to apply the gate pulse to thyristor T3, T4 only, right? Again, for the next positive half cycle, T1, T2 will be fired. For the next negative half cycle, T3, T4 will be fired. Okay, and so on. Okay, so next, let us discuss the circuit operation, right? So for omega t is equal to 0 to alpha, it is like a thyristors T1, T2 forward bias mode, but we have not applied the gate signal. So that's why thyristor T1, T2 will be in a forward blocking mode. Similarly, T3, T4 will be in a reverse blocking mode. So it is like all the 4 thyristors will be in a off state, na, right? So let me draw the circuit for omega t. For omega t is equal to 0 to alpha, it is like all the 4 thyristors will be in a off state. So equivalent circuit will be like this. All the 4 will be acting as an open switch. So whether the current will flow from source towards the load? No, current will not flow from source to the load, right? So because the closed path is not available. This is R, V0, I0, and here we're having the supply. Na? This is a Vs plus minus. Okay, this is thyristor T1. This voltage is Vt1. Thyristor T2. This voltage is Vt2. Thyristor T3. This voltage is like a Vt3. This voltage is like a Vt4. This is a IS current, supply current. This is thyristor T1 current, IT1. Thyristor T2 current, IT2. Similarly, we can indicate T3, T4, IT3, IT4 also. Okay. Next. So now current is not flowing from source towards the load. So can we say that current in the circuit will be 0, right? So I0 is equal to IS is equal to IT1 is equal to your IT2, IT3, IT4 also 0. Okay. So let me write it as directly 0 ampere, right? Next, what about the V0? V0 is equal to I0 into R, right? So V0 is equal to 0 volt. V0 is equal to 0 volt. Now my question is, what about Vt1, Vt2? Suppose for this circuit, if I want to find the Vt1, Vt2, voltage across thyristor T1, voltage across thyristor T2, what will be the Vt1, Vt2? Yes, can anyone? That is voltage between these 2 points. Voltage between these 2 points. Please consider here total potential difference is Vs volt na. That is potential difference between this point and this point. It is a Vs volt. Okay. Now you can check. Yes. Yes. We'll discuss whether it is a Vs, whether it is a minus Vs, and so on. Okay. So now we can check here. This potential higher will be appearing here. So let me write here. This is a plus. This is a minus. This full potential difference is equal to Vs volt. This potential difference is equal to Vs volt. Now across this potential difference, we are having a two switches, right? We are having a two switches, thyristor T1 and thyristor T3. Both are in a off state now. One is a forward blocking mode, second one is in a reverse blocking mode. So if you recall static VI characteristics of the SCR, during forward blocking mode, the SCR is characterized with a high voltage, less current. Means, and during the reverse blocking mode also high voltage, less current. So the meaning is this is also acting as a high impedance. This is also acting as a high impedance. Are you getting the point? So can we say that? And as we know, all the four thyristors are made up of the same material, same construction, right? More or less all the four are identical only, na, right? So can we say that the impedance offered by this switch as well as impedance offered by this switch will be same only, right? So can I say that whatever the potential difference here, this potential difference will be getting divided equally across this switch as well as this switch? Are you getting the point? Okay. Or simply you can apply KVL to this loop. You can apply KVL to this loop. You will understand. Plus Vs minus Vt1 plus Vt3 is equal to 0 na. Plus Vs minus Vt1 plus Vt3 is equal to 0. Right? So now what is the Vt1 and Vt3? As I said, both are offering the same impedance. Both are in a blocking mode only. Both are offering the same impedance, right? So can I say that these two will be getting divided equally? Okay. So can I say that Vt1 is equal to plus Vs by 2 and Vt3 is equal to minus Vs by 2. I am writing plus for Vt1 because thyristor T1 is in a forward blocking mode. Forward word is there. And thyristor T3 is in a reverse blocking mode. Okay. So that's why Vt1 is a plus Vs by 2. Vt3 will be minus Vs by 2. Right? Both are in a off state only. Right? But this voltage will be getting divided as, right, Vs by 2 and minus Vs by 2. You can check. Okay. You can simply put here this is a Vs by 2. Replace Vt1 with a Vs by 2. And here Vt3 with minus Vs by 2. Will be getting plus Vs minus Vs by 2 minus Vs by 2 is equal to 0. And it is fulfilling the requirement or the equation. Okay. Either you can apply KVL to this loop or you can apply KVL to this loop. Vs, T1, load, T2, and again back to the Vs. You can apply KVL to this loop also. You will be getting the same answer. Those thyristors which are in a forward bias mode, forward blocking mode, across those thyristors, the voltage appearing is equal to plus, that is a positive Vs by 2. The thyristors which are in a reverse blocking mode, across those thyristors, the voltage appearing is equal to minus Vs by 2. Okay. This is we are discussing only from 0 to alpha. Okay. So just like in a center adapter transformer configuration, we discussed two conclusions basically. In a center adapter transformer configuration, when both the thyristors will be in an off state, at that time the voltage appearing across each thyristor is equal to plus Vs and second one is in minus Vs. Similarly here, when all the four thyristors will be in an off state, the voltage that will be appearing across the thyristors which are in a forward blocking mode, the voltage is equal to plus Vs by 2. Those thyristors which are in a reverse blocking mode, across those the voltage appearing is equal to minus Vs by 2. Right? Next. So now, so this is for 0 to alpha. Now you can check here. Yes, the waveform during 0 to alpha, V0 is 0, I0 is 0. Okay, we have not drawn the waveform of Vt1, Vt2, but we can draw. Okay, next. So this is for 0 to alpha. Next, from alpha to pi, what will happen? At omega t is equal to alpha, we are going to apply the gate pulse to thyristor T1. Okay, so for omega t is equal to alpha to pi, for omega t is equal to alpha to pi, what will happen? Yes. So we can check at alpha, we are applying the gate pulse to thyristor T1, T2. So definitely our thyristors T1, T2 will turn on. Once T1, T2 turns on, current will be flowing from Vs, T1, load, T2, and again back to the Vs. In this loop, the current will be flowing. In this loop, the current will be flowing. Okay. So if the current is flowing into this loop, can we say that V0 is equal to Vs only, because voltage across thyristor T1 is 0, voltage across thyristor T2 is also equal to 0. Okay. Now let me draw the equivalent circuit during alpha to pi. During alpha to pi, T1 and T2 are acting as a short circuit. T3, T4 are acting as an open circuit. Okay. So let me draw the circuit diagram. T1, T2 short circuit, T3, T4 open circuit. So this is a T1. Here it is a T4. Here it is a T3. And here it is a T2. Okay. We are having a load purely resistive. Right? Vs plus minus, this voltage is Vt1, this voltage is Vt2, this is Vt3, and here we are having a Vt4. Resistance R, this is a V0, and current here is a I0, right? Yes. Let me write it as a IT1, and here it is a IT2, and here it is a IS. Now, yes, during omega t is equal to alpha to pi, current is flowing from Vs, T1, load, T2, and again back to the Vs. Vt1, Vt2 both are 0. So let me write Vt1 is equal to Vt2 is equal to 0 volt, right? Thyristors are in a forward conduction mode. Okay. Now, if can we apply KVL to this loop? Yes, I'm saying Vs, T1, load, T2, and again back to the Vs. We can apply KVL. It is a plus Vs minus Vt1 minus V0 minus Vt2 is equal to 0. Out of that, Vt1 is 0, Vt2 is 0. So can we say that V0 is equal to Vs only? Load voltage is same as that of the supply voltage. Next, what about the Vt3, Vt4 in this case? So please check. Vt3 means voltage across thyristor T3, right? So can we apply KVL to this loop? Vs, T1, T3, and again back to the Vs. Can we apply KVL to this loop? Either we can apply KVL or by observation also. Yes, we can tell what is the Vt3. Okay, let me first yes, write it the KVL. KVL will be plus Vs minus Vt1 plus Vt3 is equal to 0 na. Vs, Vt1, Vt3 like this. Okay, so Vt1 is 0. So can we say that Vt3 is equal to minus Vs? Similarly, you can check for Vt4 also. Okay, you will be getting Vt4 also equal to minus Vs. Minus Vs. Is this clear? The meaning is, out of these four, if all the four thyristors will be in a off state, the voltage appearing across the thyristors will be combination of Vs by 2 and minus Vs by 2. Out of the four, if two are in a on state, two are in a off state, those who are in a off state, the voltage appearing across them is equal to minus Vs. If they are in a reverse bias mode, it will be minus Vs. If they are in a forward blocking mode, then it will be plus Vs. Okay. So you can check the voltage across the thyristor waveform. It will be a combination of Vs by 2 and Vs. Vs by 2 and Vs. Whereas if you recall the center tapped transformer configuration, the voltage across the thyristor for purely resistive load we discussed na, right? For a purely resistive load, the voltage across thyristor waveform, it was a combination of Vs and 2 Vs, but it is a here it is combination of Vs by 2 and Vs. Okay, so now yes, so here we are having Vt4 is minus Vs, Vt3 is also equal to minus Vs. Okay, Vt3 is also equal to minus Vs. Next, so this is from alpha to pi. From pi to pi plus alpha, what will happen? From pi to pi plus alpha, supply voltage is negative, so supply voltage will be reversed. It is a minus here, plus here. Okay, so that's why it is a minus here, here it is a plus, right? So let me write for omega t is equal to pi plus alpha. For omega t is equal to pi plus alpha. Omega t is equal to pi plus alpha. Yes, it is like thyristors T3, T4 forward bias mode, but we have not applied the gate signal. Okay, so thyristor T3, T4 forward blocking mode, T1, T2 reverse blocking mode. Okay, so all the four will be in off state. right? This is a VT1, VT3, VT4, and VT2, R, V0, and I0, right? So this is like IS positive can we consider, minus plus, yes. Let me write it as a IT1, this is a IT2, right? Before that, yes, here you can check V0, we have written Vs. What is the I0 in this case? I0 is equal to V0 by R, na? So let me write here, I0 is equal to V0 by R, because load is purely resistive. So I0 is equal to Vs by R. Now, yes, is there any relation between IS and I0? Come on. For this circuit, alpha to pi, whether IS and I0 both will be same or different. You can check current is flowing like this, Vs, T1, load, T2, and again back to the Vs. So can I write IS is equal to I0? Yes or no? Right? IS is equal to I0. So let me write IS is equal to I0. That is same. Direction of IS and direction of I0 both are same here in this case. Again, can I write IT1 is equal to IT2 is equal to again IS, which is equal to I0, because the same current is flowing now. So I can write IT1 is equal to I0, IT2 is also equal to I0. Okay, so let me write here. Yes, I'm adding here. IT1 is equal to IT2 is equal to IS, which is equal to I0. Okay, this is for alpha to pi. Next, in this circuit now, you can check current will not flow from source towards the load now, right? So here can I write I0 is equal to 0 ampere. Similarly, thyristor currents IT1, IT2, again your IS is also equal to 0 ampere. All the currents will be 0. So what about the V0? V0 is equal to I0 into R. So it is a 0 volt. That is the 0 volt, right? This is the V0. I0 is 0. V0 also equal to 0, right? So you can check here. Pi to pi plus alpha, V0 and I0 both are 0. Okay. Next, similarly, we can find VT1 and VT2. Now, what is the VT1 here? Yes, thyristor T1, T2 on a reverse bias mode. Na? So all the four are in off state. So VT1 is equal to VT2 is equal to what? Minus Vs by 2. You can apply KVL to this loop. KVL to minus Vs minus VT1, right? Vs, T1, load, T2, and again back to the Vs. In this loop, you can apply KVL. You will be getting it is a minus Vs by 2, right? Next, this is from pi to pi plus alpha. Pi plus alpha to 2 pi, what will happen? For omega t is equal to pi plus alpha to 2 pi. So at pi plus alpha, we are applying the gate pulse to thyristor T3, T4. So definitely our T3, T4 will turn on. Okay, so you can check. Once T3, T4 starts conduction, current will flow from Vs, T3, load, T4, and again back to the Vs. In this loop, the current will be flowing. Okay, so let me write from pi plus alpha to 2 pi. Yes, T3, T4 turns on. So here T1 is in an off state, T4 is in an on state, T3 on state, T2 off state. Okay, and this is the load we're having, right? This is the supply voltage. Vs minus plus Is direction. This is yes, like this we have indicated. This is VT1, VT2, VT3, VT4, R, V0, I0. This is IT1 and IT2. Yes. Now, during this interval, pi plus alpha to 2 pi, the current will flow from Vs, T3, load, T4, and again back to the Vs. Yes or no? In this loop, the current will be flowing. In this loop, the current will flow. Yes or no? Right? So now you can check here. During the current flowing through the load is in a downward direction only. And if you recall from omega t is alpha to pi interval, during that interval also the current flowing through the load was in a downward direction. So here also current flowing through the load is in downward direction. In that interval also it was a downward direction. So can I say that I0 is a positive only? If I0 is positive, your V0 is also positive only. Now important thing here. Yes, you can check I0 and IS. Current is flowing like this: Vs, T3, load, T4, and again back to the Vs. I am saying back to the Vs. Means in the supply, in the source, the current direction is downward. Yes or no? Current is flowing from Vs, T3, load, T4, and again back to the Vs. Means in the supply branch. Okay. Means in this branch we can say the current direction is downward. Okay. And actually what we considered the positive source current is nothing but the upward. Okay. So can I say that when T3, T4 conducts, your IS will be negative, source current will be negative? Yes or no? Right? If you recall from alpha to pi interval, in the alpha to pi interval, when T1, T2 were in the conduction mode, at that time IS and I0 both were same, in the same direction. IS is also positive, I0 also it was a positive. But in this case, if you check from pi plus alpha to 2 pi, that is when T3, T4 conducts. When T3, T4 conducts, okay, current is flowing like Vs, T3, load, T4, and again back to the IS. Okay, back to the Vs. So in this branch, actually the current is flowing in the downward direction. So IS is a negative. Your I0 is positive, but IS is negative. Okay. So let me write here. Yes, first thing is VT3, VT4. VT3, VT4 is equal to 0 volt. Next, we can apply KVL to this loop. It is a plus Vs, right? Plus Vs minus VT3 minus V0 minus VT4 is equal to 0. Out of that, VT3 0, VT4 is also 0. So can I say that V0 is equal to Vs only? V0 is equal to Vs only. Now V0 is Vs means your output voltage is positive. Even though the supply voltage is negative, but output voltage is positive. Okay. Next, I0 is equal to V0 by R. So which is equal to Vs by R. Which is equal to Vs by R. Right. Next, now here, can I write Is is equal to minus I0? This is very important. Is is equal to minus I0 because supply current is actually flowing in the downward direction, right? And we considered a positive Is means upward direction. Okay. So Is is equal to minus I0 here, right? Next, what about the VT1, VT2 here? Can anyone? VT1 is equal to VT2. It is a Vs by 2 minus Vs by 2 plus Vs minus Vs. Yes. What is the value of VT1, VT2? Out of the 4, 2 are in on state, 2 are in off state. VT1, VT2 minus Vs, correct? It is a minus Vs, right? It is not the minus Vs by 2, it is a minus Vs. Jagta, please check. Yes, you can apply KVL or simply let, yes. Can you apply KVL to this part only? I am saying Vs, T1, T3, and again back to the Vs. To this part, can we apply KVL? If you apply KVL to this part, yes, we can get it as a minus Vs. Yes or no? Minus VT1 plus VT3 is equal to 0. No? This part I am saying. Out of that, VT3 is 0. So what it indicates? VT1 is minus Vs, na? Right? So VT1 is equal to minus Vs. Similarly, you can check for VT2 also. How to check for VT2? You can apply KVL to this part. Yes, Vs, VT2, T4, and again back to the Vs. To this loop, you can apply KVL. Okay, you'll be getting it as a plus Vs plus VT2 minus VT4 is equal to 0. So VT2 will be getting it as a minus Vs only. Is this clear? Right? So same conclusion. Out of the 4, if 2 thyristors are in a on state and 2 are in a off state, the thyristors which are in a off state, right? If they are in a reverse blocking mode, then the voltage appearing will be minus Vs. Okay, right? If all the 4 are in a off state, then those who are those thyristors which are in a reverse blocking mode, across them the voltage will be minus Vs by 2. and those are in a forward blocking mode. Across them the voltage will be plus Vs by 2. Okay, so please keep it in mind. We are having 4 switches. If all the 4 are in a off state, then the voltage will be like a plus Vs by 2 or minus Vs by 2. If out of the 4, if 2 are in a on state, 2 are in a off state, then the voltage will be, yes, it is a either plus Vs or minus Vs. It depends on whether the switch is in a forward blocking mode or it is in a reverse blocking mode. Okay, so yes, so this is, we are having V0 is equal to Vs, it is a positive only. I0 is equal to Vs by R. Okay, I0 is also positive, V0 is also positive. So from pi plus alpha to 2 pi, from pi plus alpha to 2 pi, you can check V0 is a positive, even though your supply voltage is negative, but V0 is a positive, right? I0 is in phase with the V0, right? It is a V0 by R, na? Right? So that's why it is in phase with the V0, right? So this is the circuit operation corresponding to one input cycle of the supply. Similarly, after 2 pi, the same cycle will repeat, na? You can check at 2 pi plus alpha, again the thyristor is turned on T1, T2, and the same cycle or same operation will repeat, right? So here, corresponding to positive half cycle of the supply, also we are getting the output non-zero. Corresponding to the negative half cycle of the supply, also we are getting the output non-zero. So that's why it is a full wave controlled rectifier. Why it is a controlled rectifier? Because we can control the output voltage na, by controlling the firing angle alpha. Yes or no? Right? Next, my question is, if I remove or if I replace these thyristors, if I replace these thyristors with the diodes, if I replace these thyristors with the diodes, then how will be the V0 and I0? If I replace these 4 thyristors with the diodes, then how will be the V0 and I0 waveform? Diode is uncontrolled switch. As soon as it becomes forward bias, it will turn on, na? So you can check actually the V0 waveform. If I replace these thyristors with the diode, the V0 waveform will start from 0 only, right? Omega t is 0 only. Means it is like alpha equal to 0 in the thyristor case. So always keep it in mind. If we keep alpha equal to 0, okay, for the controlled thyristor, then we will be getting the output same as that of the uncontrolled rectifier. Are you getting the point? Okay, so that is the only difference between a diode rectifier and a thyristor rectifier. Okay, so diode rectifier output is equivalent to the thyristor rectifier with alpha equal to 0 degree. With alpha equal to 0 degree. Is this clear? Right? Yes. Now let us derive the expressions. So are you getting the point? Why it is a fully controlled? Because all the 4 switches are the controlled switches. That's why it is a fully controlled. Okay. Next. So V0 average. Yes. Same expression. Whatever we derived in the case of center tapped transformer configuration. Same expression we are good. Yes, we will be getting here. You can check. Whatever the waveform for omega t is equal to 0 to pi, the same is repeating from pi to 2 pi. Na? So it is like 1 by pi integration from alpha to pi. Okay. So 1 by pi integration from alpha to pi. It is a Vm into sine of omega t into d omega t. Right? So we can write it as Vm by pi. Integration of sine is minus cos of omega t. Alpha to pi, right? So which is equal to Vm by pi into 1 plus cos alpha. This is a V0 average, right? Now what is the I0 average? V0 average by R, right? For purely resistive load, it is a V0 average by R. Okay. Next, Vm by pi R into 1 plus cos alpha. Now can we write V0 RMS? V0 RMS square root of mean of squared value, na? So it is a 1 by pi integration from alpha to pi. What is the value of V0 during alpha to pi? Vm sin omega t. So it's a square. So it will be Vm square sin square of omega t into d omega t, na? To the power 1 by 2. Square root of mean of squared value, right? So which is equal to, we can write Vm upon root pi into integration from alpha to pi sin square of omega t can be replaced with 1 minus cos of 2 omega t divided by 2, na? Into d omega t to the power 1 by 2, right? I have taken Vm square outside. This pi also I have taken outside. Next, divided by 2, we can take it outside. So it is a Vm upon root 2 pi into, it is like a omega t minus sine of 2 omega t divided by 2. Limit alpha to pi to the power 1 by 2, right? So further, this can be written as Vm upon root 2 pi into pi minus alpha sine of 2 pi 0. Okay, so plus sine of 2 alpha divided by 2 to the power 1 by 2. This is your V0 RMS. What is I0 RMS? Yes. So I0 RMS. V0 RMS by R now. What is the load power? P0 average. V0 RMS into I0 RMS. Purely resistive load we are having. Okay. V0 RMS into I0 RMS, which is equal to V0 RMS square divided by R, which is equal to I0 RMS square into R. This is a P0 average, right? Next, what is the conduction time of each thyristor? Conduction time of each thyristor. Yes. Thyristors T1, T2. Okay, these two will be in the on state from alpha to pi. Na? So what is the conduction time? Pi minus alpha by omega. Yes or no? Thyristors are in on state from alpha to pi only. So T1, T2 are in on state from alpha to pi. Here it is T1, T2 conducts. Here it is T3, T4, no? Right? Let me write it as a T3 here, T4 here. Okay. So pi minus alpha divided by omega. This is the conduction time of each thyristor. Right? Next, what is the PIV rating? PIV rating of each thyristor. Yes, PIV rating of each thyristor. We discussed. Yes, voltage across thyristor is a combination of Vs by 2 and Vs, na? So it is a V max. PIV rating is equal to V max, right? What about the circuit turn-off time? TC for each thyristor. TC for each thyristor. TC for each thyristor. Yes. Can we draw the waveform of VT1, VT2? Zero, alpha, pi plus alpha, 2 pi, and again 2 pi plus alpha, right? Yes. How is the voltage? During 0 to alpha, it is a Vs by 2, na? Forward blocking mode. Alpha to pi 0, thyristors are in a conduction mode. Pi to pi plus alpha, Vs by 2, pi plus alpha to 2 pi. It is a Vs, na? Right? So it will be a combination of this. And again, it is a Vs by 2. So let me write it as a Vs by 2. This is like your minus Vs by 2. This is a minus Vs. And this is again Vs by 2. So what is the PIV rating? Peak value of reverse voltage. It is a Vmax, na? Right? So that's why PIV rating of each thyristor is equal to Vmax, right? Vmax. You can check 0 to alpha, all the 4 are in off state. So voltage across thyristor will be combination of, yes, Vs by 2 minus Vs by 2. T1, T2 are in a forward blocking mode, so it is a Vs by 2. Pi to pi plus alpha, all the 4 are in off state, so voltage will be minus Vs by 2. Pi plus alpha to 2 pi, T3, T4 are in a conduction mode, so voltage will be minus Vs. Okay. Next, 2 pi to 2 pi plus alpha is again same as that of the 0 to alpha, right? So yes, So TC for each thyristor is equal to V max. Next, can we draw the waveform of IT1, IT2 and IS? Can we draw the waveform of IT1, IT2 and IS? Yes. Waveform of IT1, IT2. Let me draw first the waveform of I0. Right? We have already drawn the I0 waveform. Alpha pi plus alpha 2 pi plus alpha and so on, right? Yes. During 0 to alpha, what is I0? 0 na? Alpha to pi, it is like this. V0 by R. We already discussed this term. This is I0 waveform we are drawing. 0. Right? So this type of waveform we are getting. And after this again like this. Okay. This is the I0 waveform. What is IT1, IT2 waveform? T1, T2 are in on state only from alpha to pi na? So IT1 waveform will be like this. IT1, IT2 waveform. Yes. This is alpha pi plus alpha 2 pi and 2 pi plus alpha. Yes, how will the waveform of IS now? Source current 0 to alpha, all the four switches are in off state, so IS will be 0 na? So this is 0. Alpha to pi, T1, T2 conducts, so we know IS is equal to I0. So here IS will be same as that of your I0, that is a positive. Pi to pi plus alpha, all the four switches are in off state, so IS is again 0. Pi plus alpha to 2 pi, what is IS? Pi plus alpha to 2 pi, IS is minus I0 na? We have written. Pi plus alpha to 2 pi, you can check IS is minus I0. Pi plus alpha to 2 pi, IS is minus I0. So here we can write it as, yes, negative pulse we are having, right? Correct? And that's, this is after. Is this clear? After this again the same repeats. Okay. So supply current is your, yes, positive, negative. Okay. So it is not a sinusoidal AC, but it is your, you can say the AC, right? Next, I0 is a positive only for all the time, right? So this is IS, IT1, IT2 and I0 waveforms. Okay. Next, now what is the I0 RMS and IS RMS? Whether both will be same or different? Come on. Whether I0 RMS and IS RMS both will be same or different? I0 RMS and IS RMS both will be same or different? Same na, right? Yesterday also we discussed them, right? RMS means what? Square root of mean of squared value. Square of this positive is positive. Square of this positive is positive. Square of this positive is positive. Square of this negative is also positive. So you can draw the I0 square and IS square waveform, you will understand. Okay. I0 RMS and IS RMS both are same. Okay. Next. So what is the input power factor now? Yes, input power factor. Input power factor. Yes, it is a P0 average divided by Vs RMS into IS RMS. No? What is P0 average? V0 RMS into I0 RMS. And what is the, yes, this is Vs RMS as it is into IS RMS. So IS RMS, I0 RMS both are same, right? So therefore input power factor is equal to V0 RMS divided by Vs RMS, right? This is your input power factor. Is this clear? Next. So this is about the purely resistive load. So you can check center tapped transformer configuration and this bridge configuration. We are getting the same waveform. Okay. The only thing is here we require the 4 thyristors, right? And in that case, it is a 2 thyristors, and in addition, we require a center tapped transformer. Okay, secondary is having the center tapping, right? Like this. Next, let us discuss the RL load. RL load. So let me put the heading. Same single phase, fully controlled bridge configuration. Fully controlled bridge configuration. And load is a RL load. Load is a RL, right? So same circuit diagram. Supply voltage Vs. V0 and here it is I0, right? Resistors are T1, T2, T3 and T4. VT1, VT2, IT2 and IT1, right? So this the waveforms. Gate pulse to thyristors. Alpha, pi plus alpha, 2 pi plus alpha, right? So this is a gate pulse to thyristors T1, T2, and here it is a T3, T4. V0 waveform. This is for continuous conduction. And as I said, in the full wave rectifier, there is a high possibility of a continuous conduction, right? So this is a I0, right? So let me indicate here from here till here, your thyristors T1, T2 conducts in this point to this point, T3, T4 conducts, right? T3, T4 conducts. Okay, so yes, so you can check this waveform with the center tapped transformer configuration waveform, right? RL load, whatever we discussed in the yesterday's session, same waveform we are having, right? Because of the inductor, right? Inductor stores energy from alpha to theta, and after that inductor will releases the energy. Okay, inductor will release the energy. So here, let us discuss the circuit operation. Vs is Vm sin omega t. So from alpha to pi, Vs is positive, right? So Vs is positive means plus here, minus here. Let me indicate here. This is a plus, and here it is a minus. Okay. So suppose at alpha, suppose at omega t is equal to alpha, we applied the gate signal to thyristor T1, T2. So T1, T2 starts conducting immediately. So after alpha, what will happen? Yes, Vs, T1, load, T2, and again back to the Vs. Okay. In this loop, the current will be flowing, right? So V0 is equal to Vs. V0 is equal to Vs. So you can check after alpha, your V0 is the same as that of the supply voltage. This will continue till theta only. This will continue till theta only. Theta is like your near to the pi. Okay, theta is like a near to the pi. I have not shown here theta. Okay, but theta is a near to the pi, right? After theta, what will happen? After theta, yes, that is when VL becomes negative. VL becomes negative means you can check here. VL means voltage across inductor is like this, plus minus VL. Voltage across resistor is like this. When T1, T2 starts conduction, it is like a Vs minus Vr minus VL is equal to 0 now. So VL is equal to Vs minus Vr. Okay. So when your Vs is equal to Vr, at that time your VL is equal to 0. And your theta point indicates the VL is 0 only. Right? Means till theta only inductor stores energy. Na? We discussed a number of times. Right? This concept. Okay. So after theta, what will happen? After theta, inductor go on releasing the energy. Okay. So theta point is like here, somewhat here. Let me indicate. This as a theta. Okay, near to the pi it is a theta, right? It depends on value of theta. Again, it depends on the value of R and L. Value of R and L. Okay. Next, so from alpha till theta, only inductor stores energy. So during this interval, T1, T2 conducts. V0 is equal to Vs. So you can check V0 is equal to Vs. And I0, as L value is a high value. Okay, we have considered. So that's why current is a constant. Current is a constant. Okay. If the value of L is reduced, then what will happen? We'll discuss it at the end. Okay, we'll discuss it at the end, right? So continuous conduction and discontinuous conduction type thing. But generally, in a full wave rectifier, right? The high possibility of getting the continuous conduction only. But in the half wave rectifier, okay, very rare chances of getting the continuous conduction, right? So next. So after theta, what will happen? After theta, inductor starts releasing the energy. So from theta to pi, from omega t is equal to theta to pi. I'm not drawing the equivalent circuit here again. Okay. So from omega t is equal to theta to pi, what is happening? Yes, here first cycle we are not discussing. Okay. That first cycle we discussed in that case. Okay. That was only for, that was occurring only for very first time now. Okay, and in the continuous cycle, that your first cycle will not appear here. Okay, so that's why simply we are not discussing. We have started discussion from omega t is equal to alpha. Definitely the first cycle, very first cycle will be there. Very first cycle there will be there. Okay, no issue. Okay, yes. Right. Okay. Okay. Yes. So now from alpha till theta, T1, T2 conducts, right? So let me write here in short, from omega t is equal to alpha to theta. It is like a T1 and T2 are in a on state. That is a conduction mode. Inductor L stores energy. Stores energy. V0 is equal to Vs. Okay. And L is a high value. So that's why your I0 is equal to constant current. I0 is equal to constant. Okay. We discussed in the yesterday's session also. If the value of inductor is very high, so it is like a opposition offered by the inductor to the change in current is high. If the opposition offered by the inductor to change in current is high, the meaning is your current will not change at all. The meaning is we'll be getting the constant current. We'll be getting the constant current, right? So I0 is equal to capital I0, right? So here From alpha to theta, you can check from omega t is equal to alpha to theta. Yes. V0 is equal to Vs and I0 is a constant current. Inductor stores energy from alpha to theta. From theta to pi, what will happen? For omega t is equal to theta to pi. For omega t is equal to theta to pi. Supply voltage is positive only. Supply voltage is positive only. Okay. But your Vs is less than Vr here now. Vs is less than Vr. Okay. So due to that, what will happen? Our inductor will not allow the sudden change in the current. Na? So that's why inductor starts releasing through T2, Vs, T1 and again back to the load. In this loop, inductor releases the energy, right? Because inductor is not having any alternate path available to release the energy. Okay. The only option is inductor need to release the energy through T1, T2, right? Because we have not applied the gate signal to T3, T4 yet, right? So that's why inductor go on releasing the energy through T1, T2. So when inductor releases the energy through T1, T2 means again T1, T2 will be in a conduction mode only. So from theta till pi, T1, T2 conducts. Alpha to theta also, T1, T2 were in a conduction mode only. Okay. So when T1, T2 conducts and inductor releases the energy, can we say that V0 is again Vs? Yes, simply apply KVL. So V0 is equal to Vs. V0 is equal to Vs. Inductor releases energy. Releases energy. I0 is equal to capital I0, right? As the value of inductor is high, so you might be thinking that, sir, when inductor is releasing the energy, current should decrease. No, value of inductor is high, so that's why current we are getting as a constant current. Okay, but definitely inductor is releasing the energy. Okay, so I0 is equal to capital I0. Okay, I0 is equal to capital I0, V0 is equal to Vs. From theta till pi plus alpha, from theta till pi plus alpha, what will happen? You can check. From theta till pi plus alpha, supply voltage is reversed. It is minus here plus here. So supply voltage will try to circulate current in this direction. Okay, right? But here our inductor is present and you can check at omega t is equal to pi. The current flowing through the inductor is a positive. It is a I0. Na? Current is positive means current flowing through the inductor direction is in downward direction. So that's why our inductor will continue go on releasing the energy. Yes, through T2 in opposition to that of the supply voltage and through thyristor T1. Okay. T2 in opposition to that of the supply voltage and through thyristor T1 and again back to the load. In this loop, the inductors go on releasing the energy. This will continue till pi plus alpha, right? Pi plus alpha. So from omega t is equal to pi plus alpha. It is like inductor L releases energy. Inductor L releases energy. Okay, so therefore V0 is equal to Vs only, and I0 is a constant. We have already discussed. I0 is a constant current, right? So inductor is releasing the energy through which thyristor pair? T1, T2 only. Through T1, T2 only. Okay. So pi to pi plus alpha. Yes, pi to pi plus alpha. V0, you can check here. Sorry. Pi to pi plus alpha, you can apply KVL here. The inductor is releasing the energy like this. Na? So it is a minus V0 minus Vs is equal to 0, right? This should be minus Vs actually. Let me write. Minus V0 minus Vs is equal to 0. Na? So therefore V0 is equal to minus Vs. Okay. V0 is equal to negative, right? So V0 is a negative we're having. Okay. So this is from pi to pi plus alpha, right? Pi to pi plus alpha. At pi plus alpha, we are applying the gate pulse to T3, T4. Okay. So T3, T4 will turn on. T3, T4 will turn on. Once T3, T4 turns on, your T1, T2 will turn off immediately. Why? Because you can check once T3 and T4 are turning on, this highest potential of the supply is appearing here. The same highest potential will appear here because T3 is acting as a short circuit. Same highest potential will appear here. Same highest potential will appear at the cathode of T1. Right? Are you getting the point? Means when T3, T4 turns on, immediately your T1, T2 will turn off due to the reverse voltage. Due to the reverse voltage. So let me write from omega t is equal to pi plus alpha to it is like a pi plus theta. Okay, pi plus alpha to pi plus theta. Pi plus theta means this is the theta na. So just like we are having here the pi plus theta instant. Pi plus theta instant. Okay, so from omega t is equal to pi plus alpha to pi plus theta. It is like a T3, T4 will be in a on state and current will be flowing like, suppose if T3, T4 are in a on state, current will be flowing like this. T3 and T4 are in a conduction mode. Current will be flowing from Vs, T3, load, T4, and again back to the Vs. In this loop, the current will be flowing. So if the current is flowing into this loop, right? You can check. Yes, V0 is again same as that of the supply voltage. It is a positive. Right? Yes, you can apply KVL. Okay. T3, T4 conducts. Let me write first this one. Yes. So for omega t is equal to pi plus alpha to 2 pi. T3, T4 conducts. So when T3, T4 conducts, okay, at that time, yes, when T3, T4 conducts, you can apply KVL. It is a plus Vs minus V0 is equal to 0 na? Plus Vs minus V0 is equal to 0 because voltage across T3, T4 is 0. They are acting as a short circuit. Okay. So let me write it as plus Vs minus V0 is equal to 0. So this indicates V0 is equal to Vs only. V0 is equal to Vs only. Now what is happening? T3, T4 conducts means again inductor go on storing the energy. Okay. So inductor L stores energy. Inductor L stores energy, right? Because current is coming out from the positive plate of the supply now, right? That is the higher potential. So like this. So again, inductor go on storing the energy, right? So next, so this is from pi plus alpha to, let me write it as a pi plus theta first, then we'll discuss. Okay, pi plus theta. So during this interval, you can check V0 is equal to Vs. So V0 we are having is equal to Vs is actually negative, but we are getting V0 is a positive, right? V0 is a positive, right? Next, this will continue till pi plus theta, means now inductor has stored the energy. Okay, inductor has stored the energy. After pi plus theta, what will happen? That is from pi plus theta to 2 pi. Inductor will releasing the energy, right? Inductor go on releasing the energy, and when pi plus theta to 2 pi, when inductor releases the energy through thyristors T3, T4, here it is like a inductor energy and supply energy, both will be adding, na? Both will be adding, right? So let me write for omega t is equal to pi plus theta to 2 pi. Pi plus theta to 2 pi. Yes, here it is a again T3, T4 will be in a conduction mode. Inductor releases energy. Yes, so when inductor releases energy, here T3, T4 will be in a conduction mode. So what is the V0? We can apply KVL. Plus Vs minus V0 is equal to 0 na? So plus Vs minus V0 is 0 means what? V0 is Vs. So here V0 is equal to Vs only, right? V0 is a Vs. This will continue till 2 pi. After 2 pi, supply voltage polarity is again reversed. Okay, so after 2 pi, supply voltage polarity is like this. So here it is a plus, here it is a minus. So supply voltage will try to circulate current in this direction. Okay, but here we are having an inductor. So our inductor continue go on releasing the energy from 2 pi till 2 pi plus alpha through thyristors T4 and T3. But in opposition to that of supply voltage. You can check in this part the supply voltage is trying to circulate current in the, yes, we can say left to right. But here inductor will continue releasing the energy, and when inductor releases the energy from L, T4, Vs na, so in this part the current direction is from right to left. Okay, so inductor is releasing the energy in opposition to that of the supply voltage. Okay, so let me write for omega t is equal to 2 pi to 2 pi plus alpha. Yes, inductor releases energy. Okay, inductor releases energy, right? Next, so what is the V0 when inductor releases energy like this? So V0, can we apply KVL? You can check here. T3, T4 in the conduction mode and supply voltage polarity is upper terminal plus, lower terminal minus. So you can check minus V0 minus Vs na, is equal to 0. Minus V0 minus Vs is 0, right? So minus V0 minus Vs is equal to 0. So therefore, V0 is equal to minus Vs. So output voltage is a negative. Okay, output voltage is a negative. So you can check here during 2 pi to 2 pi plus alpha, 2 pi here, here it is 2 pi plus alpha. Output voltage is negative, right? So this type of waveform will be getting. So circuit operation, you can check alpha to theta, inductor stores energy, V0 is equal to Vs. Theta to pi, inductor releases energy, supply energy, inductor energy, both will be adding. V0 is again Vs. Pi to pi plus alpha, from omega t is equal to pi plus alpha. Yes, inductor releases energy in opposition to that of the supply voltage. Okay, again T1, T2 will be in a conduction mode only. So your V0 is equal to minus Vs, right? Pi plus alpha to pi plus theta, right? Pi plus alpha to pi plus theta. Okay. Thyristors T3, T4 will be in a conduction mode. T1, T2 off state. Inductor again stores energy. Okay. So V0 is equal to Vs, positive voltage. Pi plus theta to 2 pi. Inductor releases energy through thyristors T3, T4 only. And here inductor energy and supply energy, both will be adding. This will continue till 2 pi. V0 is equal to Vs. 2 pi to 2 pi plus alpha. 2 pi to 2 pi plus alpha. Inductor will continue go on releasing the energy in opposition to that of the supply energy. V0 is equal to minus Vs. Okay. So this type of waveform will be getting. So I0 we have, yes, it is a constant current we have indicated because we assume that the inductor is a highly inductor value is high. Okay. Inductor value is a high, or let me write it as a high L. High L here, right? If L value is less, what will happen? We'll discuss. Okay. So before that, let us derive the expressions for this type of waveform. We yesterday already derived the expression. Okay. What is the V0 average? What is the V0 average? Yes, V0 average. Same waveform na, right? Yesterday we discussed rate is a 1 by, you can check here. Yes. Instead of taking 0 to pi, yes, instead of taking 0 to pi, we can take from alpha to pi plus alpha, right? So it is a 1 by pi integration from alpha to pi plus alpha. It is a Vm into sine of omega t into d omega t, right? So you can simplify it as Vm by pi into integration of sine is minus cos. So minus cos of pi plus alpha plus cos alpha. No? So it will be equal to 2 Vm divided by pi into cos alpha. V0 average, right? Next, what is the I0 average here? From the I0 waveform, can we write the I0 average? Come on. What is the I0 average? Average value of the load current. Check the I0 waveform. Yes, it is a okay. Capital I0 only, right? Capital I0, correct. So because I0 is a constant current, right? So average will be its magnitude only. So let me write I0 average is equal to capital I0. I0 average is equal to capital I0. Next, further can we write V0? Okay. Further can we write V0 is equal to VR plus VL? V0 is equal to VR plus VL. Na? Out of that, what is the average value of the inductor? 0, right? VL average is equal to 0 because inductor stores energy, releases energy. Okay. From alpha to theta, VL is positive. After theta till pi plus alpha, it is a negative, na? Right? So average will be 0. So VL average is 0. So therefore, can I write V0 average is equal to VR average? Further, we can write V0 average is equal to VR average means what? I0 average into R, na? I0 average into R. So therefore, I0 average is equal to V0 average divided by R, which is equal to capital I0 only. Is this clear? this expression is required. Okay, right? This is very important. While solving the numericals, you require this expression. From waveform, we can say it is equal to capital I0. But like this, V0 is equal to VR plus VL. We can say I0 average is equal to V0 average by R. Again, this is equal to capital I0 only, right? Yes. So next, so this is the I0 average. What about the V0 RMS? RMS value of output voltage. It is a 1 by pi integration from alpha to pi plus alpha. Recall the V0 waveform, alpha to pi plus alpha. It is a Vm square into sin square of omega t into d omega t, right? To the power 1 by 2. To the power 1 by 2. So we can write it as Vm upon root pi into, this can be written as integration from alpha to pi plus alpha. Sin square of omega t can be replaced with 1 minus cos of 2 omega t divided by 2 into d omega t to the power 1 by 2. So this can be written as Vm upon root 2 pi into, let me write it as a pi plus alpha minus alpha, that is a pi. Okay, right? Pi plus omega t na here, right? So pi plus alpha minus alpha, that is a pi, minus sine of 2 pi plus alpha, that is minus sine of 2 pi plus 2 alpha divided by 2 plus sine of 2 alpha divided by 2 to the power 1 by 2. So this will get cancelled out. Root pi will get cancelled out. So it is a Vm by root 2, which is equal to same as that of the Vs. V0 RMS is equal to Vs only. Okay, V0 RMS is equal to Vs. Next, what about the I0 RMS? You can check the waveform of I0. Yes, what will the value of I0 RMS for this waveform? We discussed it yesterday. If I0 is a constant, what is its RMS value? Square root of mean of squared value, na? You can simply square it. What is the square of capital I0? It is I0 square. What is the average of that? It is I0 square only. So under root that, it is a I0 only. Yes or no? So please keep it in mind. If the waveform is a constant, its I0 average and its I0 RMS both will be same. Okay, I0 RMS is equal to capital I0, which is equal to I0 average, which is equal to V0 average divided by R only. Is this very clear to all? Because we know I0 average is also capital I0. I0 RMS is also capital I0. So can we say that I0 RMS and I0 average both are same? For a flat DC waveform, RMS value and average value always, yes, both are always same, right? And which is equal to V0 average by R. Okay. Next, what is the conduction time of thyristor? Yes, conduction time of thyristor. Yes, can anyone? Conduction time of thyristor. T1, T2 are in on state from alpha to pi plus alpha, na? So it is like a pi plus alpha minus alpha divided by omega. Plus minus alpha gets cancelled out. So it is a pi by omega, right? So this is a conduction time of thyristor, right? Conduction time of thyristor. Is this clear? Next, now, what is the PIV rating of thyristor? PIV rating of thyristor. You can check in the intervals. Yes. In the intervals, we are having at least 2 thyristors will be in on state, na? Whether, yes, you can check this waveform. Alpha to pi plus alpha, T1, T2 are in conduction mode. Pi plus alpha, 2 pi plus alpha, T3, T4 conduction mode. So every time, yes, we'll be having a 2 thyristors are in on state, na? So what is the voltage across the thyristor waveform? It is like a 2 times Vs waveform only, right? Let me draw the waveform. Voltage across thyristor, and after that we'll write the PIV. Let me draw the waveform of VT1, VT2. Zero, alpha, pi plus alpha, 2 pi plus alpha and so on, right? Yes. 0 to alpha to pi to pi plus alpha, and 2 pi to 2 pi plus alpha. This is 2 Vs. This is minus, sorry, this is Vs. This is minus Vs. And this is also Vs. So what is the PIV rating? V max, no? Here, for the thyristor voltage waveform, you will not get the combination of Vs by 2 and Vs, because every time at least 2 thyristors, okay, will be in a conduction mode. So you can check between 0 to alpha in the continuous case, between 0 to alpha, just like we're having 2 pi to 2 pi plus alpha, na? This is 2 pi plus alpha, this is 2 pi. During 2 pi to 2 pi plus alpha, T3, T4 conducts. So same 2 pi to 2 pi plus alpha means again 0 to alpha, na? Right? So here also T3, T4 conducts. When T3, T4 conducts, at that time, what is the VT1, VT2? It is a Vs, na? T1, T2 forward bias mode. Okay, but forward blocking mode. Okay, we have not applied the gate signal. So that's why that will be your Vs here. Alpha to pi plus alpha, let me write. Yes, alpha to pi plus alpha should be there, because thyristors T1, T2 on a conduction mode from alpha to pi plus alpha. Please correct it. Yes. So alpha to pi plus alpha, T1, T2 in a conduction mode. From pi plus alpha to 2 pi, T3, T4 conduct. So voltage across T1, T2 will be like, yes, minus Vs, na? Minus Vs will be getting, right? And the same repeats. Okay. Yes. Yeah. So this is, yeah, let me write. PIV rating is Vmax, na? PIV rating is equal to Vmax. What is the circuit turn-off time? TC for thyristor. TC for each thyristor. Yes, what is the TC for each thyristor? Current flowing through thyristor T1, T2 becomes 0 at pi plus alpha, na? Right? And after that, the reverse voltage will be maintained till 2 pi only. So circuit turn-off time is 2 pi minus pi plus alpha divided by omega, na? Right? So 2 pi minus pi plus alpha divided by omega, right? So which is equal to 2 pi minus pi, that is a pi minus alpha divided by omega. This is the circuit turn-off time for each thyristor. Okay, circuit turn-off time for each thyristor. Is this clear? Right? Next, so this is when your REL value is high. This is when your REL value is a very high. Now suppose if we reduce the value of REL, then what will happen? Let us discuss. Okay, so REL means L value actually. Okay, so case 2 for low value of low inductor, for low value of inductor. Okay, what will happen? So it is a discontinuous conduction. Discontinuous conduction. Yes. Yes, before that, just a minute. How is the waveform of IS in this case? Waveform of IS. I0, we're having this type. How is the waveform of IS? Come on. Between alpha to pi plus alpha, IS is positive or negative? During alpha to pi plus alpha, IS will be plus I0 or minus I0. When T1, T2 conducts, IS is equal to I0, na? Yes or no? When T1, T2 conducts, IS and I0 both will be same, both will be positive. When T3, T4 conducts, IS is negative, right? So alpha to pi plus alpha, is is like your plus I0. Pi plus alpha to 2 pi plus alpha, is is like minus I0. And again here in the continuous cycle, it will be like this. This is a plus I0. This is a minus I0. Is this clear? Please check. In a resistive load also we discussed when T1, T2 are in a conduction mode, your is is equal to what? I0. When T3, T4 are in a on state, is will be equal to minus I0. Okay, is is equal to minus I0. So nature of your source current, it is a yes square wave. It is a square wave, right? Yes. So next, for low value of inductance, what will happen? For low value of inductance, so it is like we'll be having a discontinuous conduction. Discontinuous conduction. So let us discuss what will happen for discontinuous conduction. Okay, so I'm drawing only V0 I0 waveform. Alpha, pi, beta, pi plus alpha, 2 pi, and so on, right? Yes. I0 from alpha to theta, it will increase, right? After that, it will decrease. At beta, it reaches 0. So like alpha, the theta means this point somewhere here. This is pi, this is beta, pi plus alpha, and here it is 2 pi. Are you getting the point? So for discontinuous conduction means the value of the inductor is less here, so that the inductor is not releasing the energy till pi plus alpha. Okay, so inductor energy becomes less than that of the supply energy. Okay, at beta only. So from beta to pi plus alpha, your circuit will be at the rest position. Okay, so you'll be getting this type of waveform. You can check if beta is equal to pi plus alpha, we'll be getting the continuous conduction. Yesterday we discussed it. Okay, if beta equal to pi plus alpha, we'll be getting the continuous conduction, right? If beta is less than pi plus alpha, if beta is less than pi plus alpha, conduction will be the discontinuous. What is this beta indicates? Beta means what? Extinction angle, na? Beta means the extinction angle, right? So yes, so we'll be getting this type of waveform from alpha to beta. In that also alpha to theta, inductor stores energy. Theta to beta, inductor releases energy. From theta to beta, in that again we're having the two intervals, theta to pi and pi to beta. Between theta to pi, inductor energy, source energy assisting. Okay, pi to beta, inductor is releasing the energy in opposition to that of the supply voltage. Is this clear? Right? Next. So, and from beta to pi plus alpha, circuit will be at the rest position, because yeah, we have not applied the gate signal to the next thyristor pair, that is the T3, T4, and inductor energy becomes less than that of the supply energy, right? So due to that, till beta only will be having a conduction. From beta to pi plus alpha, circuit will be at the rest position. Current will not flow in the circuit, right? All the four thyristors will be in an off state from beta to pi plus alpha. At pi plus alpha, again T3, T4 conducts, and again the same cycle repeats, same operation, right? Same steps repeats, right? So this is for low value of inductor. Okay, discontinuous conduction, right? Discontinuous conduction. Please try to understand difference between this waveform and this waveform. Okay, this is a continuous conduction and this is a discontinuous conduction, right? Next, if I further increase the value of beta, if I further increase the value of inductor, let us consider it as a moderate inductor. Then what will happen? Yes, we'll be getting the continuous conduction only. But the thing is, the current will be like a decreasing, increasing, decreasing, increasing like nature. Whatever we discussed in the yesterday session, right? So we'll be getting increasing, decreasing type nature current. But in that current also, for all the time, okay, for all the time, current will be non-zero. Current will be non-zero. Here we're having the zero intervals, na? from beta to pi plus alpha, it is a zero interval. So that's why it is a discontinuous conduction, right? Okay. So this is the case 2 for low value of the inductor, right? Next. Now let us discuss for RL load and with freewheeling diode what will happen. Yes, can anyone for RL load and freewheeling diode? Suppose we are having, now if I add the freewheeling diode in this circuit, what will be the change in V0 waveform? Come on. If I add the freewheeling diode into this circuit, what will be the change in the V0 waveform? Whether the negative pulse will be getting. Yes, recall why we connected the freewheeling diode across the RL load. In a single phase half pure rectifier, we discussed the RL load with freewheeling diode. What is the drawback of this circuit RL load without freewheeling diode? The drawback is we are getting the negative pulse now. So average voltage here compared to that of the average voltage in a purely resistive case, here the average voltage will be lesser. So in order to increase, in order to improve that V0 average, we are connecting the freewheeling diode na across resistor. So you can check if the freewheeling diode is connected here, then what will happen? From pi to pi plus alpha, inductor will go on releasing the energy na through the freewheeling diode. So during that interval, what is the V0? V0 is equal to 0 volt na, right? So same thing. So let me draw the waveform here for RL load with freewheeling diode. Yes. 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 Increases output voltage. Good. Next. So here let me yes. Same, we are having fully controlled bridge configuration. Fully controlled bridge configuration. RL load and with the freewheeling diode, right? With the freewheeling diode. With the freewheeling diode, right? So same circuit diagram. The only thing is we need to add the diode. Vs, right? Resistors are T1, T2, T3, T4 R L with freewheeling diode. With the freewheeling diode. Let me indicate the freewheeling diode. DF, that is a freewheeling diode, right? So this is your I0. Okay. So this is the IS. IDF. Let me write here. IDF. Freewheeling diode current. So the waveforms. Vs 0 to pi, pi to 2 pi, 2 pi to 3 pi, right? Ig1, Ig2, Ig3, Ig4, again Ig1, Ig2. This is Ig1, Ig2, Ig3, Ig4, and again Ig1, Ig2, right? So, V0 waveform. Now V0 will not, V0, yes, will be positive only. It will not be having the negative pulse here, because inductor will release the energy through the freewheeling diode from pi to pi plus alpha, right? Alpha, pi, pi plus alpha, 2 pi, 2 pi plus alpha, and here it is a 3 pi, right? I0 will be constant current. Right? So, yes, which devices should be in a conduction mode? Let me indicate from here to here, T1, T2. Here it is a freewheeling diode, DF. From this point to this point, T3, T4. And again, here it is a freewheeling diode, right? Freewheeling diode. Okay. So you can check here from alpha to pi, the same operation as that of the previous case. The only thing is from pi to beta, when inductor releases the energy, inductor will release energy through the freewheeling diode. That is the only change. Okay, that is the only change. Okay, let me write for different intervals. Okay, which devices will be in a conduction mode and what is the output voltage value, right? So yes, at alpha we are going to apply the gate pulse to T1, T2 now, right? So at or from omega t is equal to alpha to pi. I am writing directly alpha to pi, in that alpha to theta and theta to pi actually we are having. Okay, but let me write it as alpha to theta, alpha to pi. So here V0 is equal to Vs, T1 and T2 conducts. T1 and T2 conducts. Yes or no? Right? So you can check alpha to pi, T1, T2 conducts. In that alpha to theta, actually inductor stores energy. Theta to pi, inductor releases energy from T1, T2, right? And Vs energy and inductor energy both will be adding, right? Next, so V0 is equal to Vs. Here you can check T1 and T2 conducts. Okay, T1 and T2 conducts, right? Next, for omega t is equal to pi plus alpha, what is happening? During pi to pi plus alpha, inductor is releasing the energy through the freewheeling diode. So when inductor releases the energy through the freewheeling diode, at that time V0 is equal to voltage across conducting diode. What is the voltage across conducting diode? It is a zero, na? Right? So that's why here we'll be having V0 is equal to 0. V0 is equal to V0. And which device will be in a conduction mode? Freewheeling diode. That is a DF conducts. DF conducts. V0 is equal to 0, not V0 is equal to 0. Here it should be. Yes, voltage across conducting diode, it is a 0 volt, and freewheeling diode conducts. Here T1, T2 will be in off state. T1, T2 will be in off state. Now my question is, what about the IS value? During alpha to pi, what is the IS value? During alpha to pi, what is the value of IS? Whether it will be same as that of the load current or different? During alpha to pi, what is IS? Come on. Yes, alpha to pi. IS is I0 only, right? IS is a I0, right? So let me write the IS also here. IS is equal to I0 from alpha to pi. From pi to pi plus alpha, what is IS? From pi to pi plus alpha, what is IS? Because only freewheeling diode is in a conduction mode. All the four remaining devices are in off state, na? So what is the IS? IS should be 0. Yes or no? IS should be 0. Yes or no? IS is a 0. Is this clear? Right? So because these four are in a off state, inductor is releasing the energy through the freewheeling diode. Okay, only freewheeling diode is in a conduction mode, so IS will be your 0 only. Okay, so let me write it as IS is equal to 0 ampere. IS is equal to 0. So this is from pi to pi plus alpha. So you can check from alpha to pi, V0 is same as that of the supply voltage. I0 is equal to I0. Pi to pi plus alpha, V0 is 0. Freewheeling diode is in a conduction mode. And what is I0? I0 is equal to again capital I0. Pi plus alpha to 2 pi, what will happen? From omega t is equal to pi plus alpha to 2 pi. Yes, from pi plus alpha to 2 pi, which two devices will be in a conduction mode? Come on. Pi plus alpha to 2 pi, which two devices will be in a conduction mode? Yes, it is a T3 and T4, na? Right? T3, T4 conducts, right? T3, T4 conducts. Okay, so let me write a T3, T4 conducts. So when T3, T4 conducts, when T3, T4 conducts, yes, what is the V0? V0 is same as of the supply voltage, na? Right? V0 is equal to Vs, because T3, T4 conducts, supply voltage is actually negative, na? So minus here, plus here. You can apply KVL and check. Okay, V0 will be getting it as a positive voltage. So V0 is equal to Vs. What about I0? During this interval, what is IS? Not I0, what is IS? During this interval, pi plus alpha to 2 pi, what is the IS? Please check the circuit operation. When T3, T4 conducts, freewheeling diode is in an off state. What is the IS and I0 relation? I0 is your constant current only, no matter, right? Doesn't matter. So if I0 is a constant current during T3, when T3, T4 conducts, please check what is the IS and I0 relation. Whether IS, I0 both will be same, both will be opposite. Come on. IS is equal to minus I0, na? IS is equal to minus I0. You can check. When T3, T4 conducts, actually the current is flowing from Vs, T3, load, T4, and again back to the Vs, na? So in this loop, if you check, the load current is in a downward direction only, but the source current is also in a downward direction. So actually source current is a negative here, right? So your IS is minus I0. This is very important. IS is a minus I0. Next, for omega t is equal to 2 pi to 2 pi plus alpha, what will happen? For omega t is equal to 2 pi to 2 pi plus alpha, what will happen from 2 pi to 2 pi plus alpha? Freewheeling diode conducts, na? So what is a V0? When freewheeling diode conducts, what is V0? It is like a freewheeling diode will be in on state. So voltage across load is equal to voltage across freewheeling diode, na? So that is equal to 0. So V0 is equal to 0 volt. What about the IS here? Come on. IS will be during 2 pi to 2 pi plus alpha, IS will be whether it is I0, minus I0 or 0 ampere. Yes. Zero, na? Right? It is a 0 only. Correct? It is a 0 only. Because all the 4 switches are in off state, only freewheeling diode is in a conduction mode, right? So therefore here IS is equal to 0 ampere. IS is equal to 0 ampere, right? So now you can check the source current waveform here, right? Because they asked the question for single phase fully controlled rectifier, RL load and freewheeling diode current. What is the nature of the source current waveform? We already discussed the without freewheeling diode. In that case, the source current waveform was square wave. But in this case, it is not a square wave, right? We need to draw the waveform. Okay, you will understand it is a quasi square wave, right? Why it is a quasi square wave, we will discuss. Okay, so is this clear? So circuit operation, let me summarize it as T1, T2 conduction mode, right? Inductor stores energy. After pi till pi plus alpha, inductor releases the energy through the freewheeling diode. During that case, V0 is equal to 0 volt. Okay. Next, pi plus alpha to 2 pi, T3, T4 conducts. Inductor go on storing the energy. Okay. Actually, it is from pi plus alpha to pi plus theta only inductor will store. Okay. V0 is equal to Vs. From pi plus theta to 2 pi, inductor releases the energy, right, through same thyristors, T3, T4. So again, V0 is equal to same your Vs only, right? And after 2 pi till 2 pi plus alpha, freewheeling diode conducts. Okay, right? So only change compared to the previous case, if you check the change in the operation is only from pi to pi plus alpha and 2 pi to 2 pi plus alpha. Here we are having the freewheeling diode will be in a conduction mode. Okay, freewheeling diode will be in a conduction mode. Now this V0 is same as that of the purely resistive load, na? So we have already derived the expression of V0 average, right? So no need to derive here again. Okay, so because same expression, same waveform, we have derived the expression of V0 average already. Okay, so no need to derive. So I will directly draw the IS waveform here. That is the important IS waveform, source current waveform. Yes, from 0 to alpha, alpha to pi, pi to pi plus alpha, and pi plus alpha to 2 pi. Yes, during 0 to alpha, IS is same as that of whatever we are having 2 pi to 2 pi plus alpha, na? Okay, so let me write as 2 pi to 2 pi plus alpha also. So 2 pi plus alpha. So during 0 to alpha, IS is 0 because freewheeling diode is in a conduction mode. Because from 2 pi to 2 pi plus alpha also freewheeling diode was in a conduction mode. So that's why in a continuous cycle, 0 to alpha will be same as that of your 2 pi to 2 pi plus alpha. Alpha to pi, T1, T2 conducts, IS is equal to plus I0. Pi to pi plus alpha freewheeling diode conducts, IS is 0, na? Pi plus alpha to 2 pi, yes, IS is a minus I0. T3, T4 conducts, and from 2 pi to 2 pi plus alpha, freewheeling diode conducts. Okay, so this is like a plus I0 and this is a minus I0. So nature of source current. Source current here is quasi square wave. This is not a square wave, this is a quasi square wave. Quasi square wave. Is this clear? This is a quasi square wave, right? Yes. So keep it in mind, for REL load without freewheeling diode, source current waveform is a square wave. With the freewheeling diode, source current waveform is a quasi square wave. Okay, right? For purely resistive load, we don't have a square wave, na? For purely resistive load, we are having a changing current, right? So alpha to pi, positive current in phase with the V0, and pi plus alpha to 2 pi, it is a negative current we are having. Okay, right? So okay, we'll take a break here. After the break, we'll discuss about the RE load and RELE load. Don't miss the RELE load specifically, right? Because most of the time they ask the question on RELE load. They will give the RELE load and they said that they generally give the statement like if a load is highly inductive, okay, RELE load and EL value is high, then what is the difference between that and REL load with high inductor? We'll discuss. Okay, right. So we'll take a break here. We'll start at 7:25, right? Okay.
Hello, sir.
Okay. So now let us discuss full wave controlled rectifier bridge configuration with the RE load. Okay. So fully controlled bridge configuration. RE load. Yes. Okay. VS is a E so this point is like theta. This point is like pi minus theta. Okay. This is a 2 pi plus theta and 2 pi minus theta. Here it is. Okay. Suppose at this instant we are applying the gate pulse Ig alpha pi plus alpha, right? So this is like a gate pulse to thyristors T1, T2. So Ig1, Ig2 here. This is a gate pulse to Ig3, Ig4, and again the gate pulse to Ig1, Ig2. Right? So this is a 2 pi plus alpha. V0 So initially the V0 is E only. So this is the E, this is the Vs. Okay, and I0 is like this. This is like your Vs minus E divided by R. Right? Okay. So let me write the instance. This is alpha. This is like a pi minus theta. Here it is a 2 pi plus alpha. This instant is like your, let me write here, 2 pi minus theta. And this is a, sorry, this is pi plus alpha. And that one is 2 pi minus theta. Right? Next. This is a 2 pi plus alpha. And here it is a 3 pi minus theta. Right? Pi plus alpha. This is a 2 pi minus theta. Okay? Right? Okay. So now let us discuss the fully controlled bridge configuration with the RE load. Okay, RE load. Now in the load we are having only resistor and a inductor, only resistor and a EMF E. Okay, we don't have an inductor. So as the inductor is not there, so there is a no point like storing energy and releasing energy. Okay, so simple elements we are having resistor and a EMF E. Already we discussed the single phase half wave control rectifier with RE load. Okay, the difference between the two, if you check the half wave control rectifier RE load, okay, so we had from omega t is equal to 0 to pi, we are having the same waveform, but from pi to 2 pi we are having only E. If you recall that waveform, okay, you can check, only E we were there. Okay, we were having there, but now corresponding to the negative half cycle also we'll be getting this pulse. Okay, why we are getting this pulse, let us discuss. So we're having a Vs is equal to Vm into sine of omega t. Vs is equal to Vm into sine of omega t. That is a positive, negative, positive, negative. Okay. So E is the constant voltage E. That is, it is like RE load means a battery charging circuit. RE load means a battery charging circuit. Okay. Keep it in mind. R load means it is like just your electric heater load. Heater load. Okay. RE means your battery charging circuit. Okay. Next. So Vs is positive 0 to pi, pi to 2 pi, Vs is negative. Okay. And E is the constant voltage. So suppose when Vs is positive, the polarity will be plus here and minus here. So let me write it as, this is the plus and here it is a minus. So this plus will appear here, this minus will appear here. Okay. So you can check at this side, we are having the voltage is Vs. At this side, we are having the voltage is Vs. Also at the load side, we are having the voltage is E. At the load side, we are having the EMF E. And these two will be opposite. Now these two will be now opposite. So now can we say that when Vs is greater than E, when Vs is greater than E, then and only then our thyristors T1, T2 will be in a forward bias mode. You can check. If I remove this E, it is like when Vs is positive, our thyristors T1, T2 will be in a forward bias mode. When I am saying when we remove E, okay. But if E is present, if E is present means what? In the load we are having now opposite EMF. We are having the opposite EMF. So if your supply voltage becomes greater than that of the E now, then and only then our thyristors T1, T2 will be in a forward bias mode. T1, T2 will be in a forward bias mode. Okay. So let me write here, when Vs becomes greater than E, then it is like a T1 and a T2 will be in a forward bias mode. Forward bias mode. Please try to understand this one. Okay. You can compare this circuit with a purely resistive load. If a E is not there, suppose if E is not connected, then what generally we are saying, when Vs is positive, T1, T2 forward bias. But now in the load we are having a EMF E, and that EMF is like a opposite to that of your V0 polarity. Na? V0 is plus here minus here, and EMF is actually it is trying to circulate current in the upward direction. So if your Vs is greater than E, then and only then your T1, T2 will be in a forward bias mode. You can check if the supply voltage is less than the E, na, current will not flow through the thyristors T1, T2 because these two will be in a reverse bias mode. Similarly, suppose when Vs is negative, then what will happen? When Vs is negative means it is a minus here plus here. So this minus will appear here, this plus will appear here. So when Vs is negative, we are having T3, T4 in the picture. Na? Now you can check, even though the Vs is negative, but the higher potential is appearing at the thyristor T3. So here, when the magnitude of Vs is greater than E, then our T3, T4 will be in a conduction mode. I am saying the magnitude of Vs. Okay. Because even though the Vs is negative, but we have connected the thyristors in such a way that when Vs is negative, T3, T4 will be in a forward bias mode, right? But here we are having the EMF. So unless and until your supply voltage becomes greater than the E, okay, our thyristors T3, T4 will not switch into the conduction, will not switch into the forward bias mode. Okay. So let me write here, when mod Vs is greater than E, mod Vs means this is only for negative value of Vs I am writing, okay, is greater than E, then T3 and T4 will be in a forward bias mode. Forward bias mode. Let me write it as, yes. This is for omega t is equal to 0 to pi, and this one is for omega t is equal to pi to 2 pi. That is when Vs is negative. Okay, so please try to understand. So whatever I told you, when Vs is positive and if the value of Vs is greater than E, then and only then our thyristor T1, T2 will be in a forward bias mode. When Vs is negative and if the magnitude of Vs is greater than E, because you can check E is here we are having a positive, and Vs negative means this negative half cycle we are having it as a Vs negative. So if you compare only, this is positive and this will be negative now. So that's why here we need to compare the magnitudes. So that's why I have here drawn the dotted, okay, corresponding to the negative half cycle of the supply. I have drawn the mirror image, that is the dotted one. Okay, that indicates same shape. The only thing is the positive I have drawn. Okay, so that we can compare this value, this Vs and this EMF. Okay, so here when mod Vs is greater than E, T3, T4 will be in a forward bias mode. Now you can check here. We are having the intervals like 0 to theta, theta to pi minus theta, pi minus theta to pi, pi to pi plus theta, pi plus theta to 2 pi minus theta, 2 pi minus theta to 2 pi. So in that case, you can check during 0 to theta, Vs is less than E. Yes or no? Let me write during 0 to theta for, yes, omega t is equal to 0 to theta, Vs is less than E. If Vs is less than E, thyristors T1, T2, reverse bias mode. T1 and T2 reverse bias mode now. Reverse bias. Okay. Next, for omega t is equal to theta to pi minus theta. From theta to pi minus theta, if you check, pi minus theta means this instant. So from theta to pi minus theta, Vs is greater than E. Okay. So Vs is greater than E. So it is like a thyristors T1 and T2 forward bias mode. Forward bias mode, right? Means we can apply the gate signal to the thyristor at any instant between theta to pi minus theta. Okay. Next, so T1, T2 forward bias. Next, you can check from pi minus theta to pi, Vs is less than E na. From pi minus theta to pi, Vs is less than E. For omega t is equal to pi minus theta to pi, it is like a Vs is less than E. So when Vs is less than E, again T1 and T2 will be in a reverse bias mode na. Reverse bias mode, right? T1, T2 will be in a reverse bias mode. This is from 0 to pi we discussed. Similarly, from pi to 2 pi, let us discuss. So from pi to 2 pi, from pi to pi plus theta, from pi to pi plus theta, this dotted one indicates the magnitude of Vs is less than E. From pi to pi minus, from pi to pi plus theta, mod Vs is less than E. Okay, so for, yes, let me write here. Yes, for omega t is equal to pi plus theta, mod Vs is less than E. Supply voltage is actually negative na here. Okay, mod Vs is less than E. So what about T3, T4? T3 and T4 reverse bias. Reverse bias. Okay. From pi plus theta, for omega t is equal to pi plus theta to 2 pi minus theta. You can check pi plus theta means this instant. Till this instant means 2 pi minus theta. Pi plus theta to 2 pi minus theta. Vs is greater than E. That is a mod Vs. Okay. So mod Vs is greater than E. So what about thyristor T3, T4? T3 and T4 will be in a forward bias mode. Forward bias. Okay. And similarly for omega t is equal to 2 pi minus theta to 2 pi. So during this interval 2 pi minus theta to 2 pi, if you check 2 pi minus theta is here and 2 pi is here. Mod Vs is less than E na, right? So we can write mod Vs is less than E. So T3 and T4 will be in a reverse bias mode. Now you can check reverse bias mode. So if you check between 0 to pi and pi to 2 pi, T1, T2 are in a forward bias mode only during this interval na? That is theta to pi minus theta, right? Means actual the current will be flowing into the circuit only from only during this interval, that is theta to pi minus theta. Whereas if you check during the negative half cycle, T3, T4 are in a forward bias mode only during pi plus theta to 2 pi plus theta, right? Because in the load varying only R and E, we don't have the inductor here. Are you getting the point? Okay. So that's why we need to apply the gate pulse to thyristor only when they become a forward bias. Okay. So between theta to pi minus theta, we're going to apply the gate pulse to thyristor T1, T2. And between pi plus theta to 2 pi minus theta, we're going to apply the gate pulse to T3 and T4. Are you getting the point? Okay. So therefore you can check, suppose that omega t is equal to alpha. That's why we have selected the alpha na. You can check this alpha is greater than theta. Alpha is greater than theta na, right? So if I apply the gate pulse before theta, whether T1, T2 will turn on? No, because T1, T2 will be in a reverse bias mode na. So that's why even though if I apply the gate pulse to thyristor T1, T2 before less than theta, thyristors T1, T2 will not turn on. So we need to apply the gate pulse only after theta. So that's why I have applied the gate pulse at alpha, at omega t is equal to alpha, right? Now you can check. So between 0 to alpha, we're having the two intervals. One is a 0 to theta and second one is theta to alpha. So between 0 to theta, thyristor T1, T2, you can check between 0 to theta, T1, T2 are in a reverse bias mode. Okay. So even though we apply the gate signal, means reverse bias means thyristor T1, T2 are in a off state. So when T1, T2 are in a off state, T1, T2 are in a off state, whether the current will flow into the circuit, you can check here. Vs is positive, negative, plus, minus. Na? Between 0 to theta, Vs is less than E. T1, T2 are in a reverse bias mode. So whether the current will flow from source to load? No. So what is the V0? V0 is equal to E. Na? Same thing we discussed in the half wave rectifier, half wave control rectifier, na? Right? So 0 to theta, V0 is equal to E only. Is this clear? Because T1 and T2 are not in a T1 and T2 will be in a reverse blocking mode. Reverse blocking mode. Okay. So let me write here. For omega t is equal to 0 to theta, T1 and T2 will be in a reverse blocking mode. Reverse blocking mode, because Vs is less than E. Na? Vs is less than E. So T1, T2 are in a blocking mode, means current will not flow into the circuit, right? So that's why your I0 is equal to 0 ampere, right? If I0 is 0, what about the V0? You can check RE load we are having. What is the V0? V0 is equal to I0 into R plus E. Na? V0 is equal to I0 into R plus E. I0 is 0. So V0 is equal to E. Na? Yes or no? RE load. If load current is 0, V0 is equal to R. You can apply KVL to this loop. It is a plus V0 minus I0 into R minus E is equal to 0. Na? Right? So let me write it as plus V0 minus I0 into R minus E is equal to 0. Out of that, I0 is 0. So therefore, V0 is equal to E only. So you can check between 0 to theta, V0 is E, I0 is 0 ampere. Between 0 to theta means this point somewhere here. 0 to theta, V0 is E, I0 is 0. Is this clear? Right? Current will not flow into the circuit. Theta to alpha, you can check after theta, Vs is greater than E. But we have not applied the gate signal. Na? So between theta to alpha, what is the mode of operation of thyristor T1, T2? Come on. Between theta to alpha, what is the mode of operation of thyristor T1, T2? Yes, whether they will be in a reverse blocking, whether they will be in a forward blocking, whether they will be in a forward conduction. Come on. Between theta to alpha. Forward blocking, yes or no, right? Good. So these two will be in a forward blocking. So let me write here. For omega t is equal to theta to alpha, thyristors T1 and T2 will be in a forward blocking mode. Forward blocking mode. Okay, forward blocking mode, right? So T1, T2 are in a forward blocking mode means what? Again, T1, T2 are in a off state only. Na? T1, T2 are in a off state. So whether the current will flow from source towards the load? No, current will not flow from source towards the load. So I0 is 0. What is the V0? V0 is E only. Okay. So I0 is 0 and V0 is equal to E. V0 is equal to E. Is this clear? I0 is 0 and V0 is equal to E. Next. Now, so from alpha to pi minus theta, from omega t is equal to alpha till pi minus theta. Pi minus theta means this instant. So from alpha to pi minus theta means now we applied the gate pulse to thyristors T1, T2. So definitely T1, T2 will turn on. Okay. So current will be flowing from Vs, T1, load, T2 and again back to the Vs. In this loop, the current will be flowing. Right? So if you check if the current is flowing into this loop, what is the V0? V0 is equal to Vs only, na? Right? You can apply KVL plus Vs minus V0 is equal to 0, right? Plus Vs minus V0 is equal to 0. So what is V0? V0 is equal to Vs only, right? So let me write here. For omega t is equal to, for omega t is equal to alpha to pi minus theta. Alpha to pi minus theta. Yes, thyristor T1 and T2 will be in a forward conduction mode. Forward conduction mode. Forward conduction mode. Okay. So alpha to pi minus theta, T1, T2 are in a forward conduction mode, na? Right? So current is flowing from Vs, T1, load, T2 and again back to the Vs. Okay. V0 is equal to Vs. V0 is equal to Vs. What is I0? You can check V0. We are having, apply KVL to this loop. You will be getting plus V0 minus I0R minus E is equal to 0 now. So we can write plus V0 minus I0 into R minus E is equal to 0. So therefore, what is I0? I0 is equal to V0 minus E by R. Na? What is V0? Vs. So that's why we can write it as a Vs minus E by R. Is this clear? This is your I0. This is the I0. So that's why I have written here. It is equal to, yes, not here. Yes, Vs minus E by R. Na? So that is nothing but V0 minus E by R, right? So now you can check from theta to pi minus theta. Your I0, definitely V0 is equal to Vs, same as that of the supply voltage. What about the I0? I0 is equal to Vs minus E by R. So you can check at alpha. Alpha means this point, na? So corresponding to alpha, if you check, here we will be having the alpha. Corresponding to alpha, we are having the supply voltage is here. So you can check here supply voltage is Vm sin alpha, na? Vm into sin of alpha, and E is here. So Vs minus E, the difference will be non-zero. So that's why load current is Vs minus E by R, na? So that non-zero voltage divided by R. So that's why here we will be having sudden increase in the load current. Sudden increase in the load current. After alpha, you can check. This is alpha, na? After alpha, you can check. Vs is like this. So Vs minus E difference is non-zero. So that's why your current is non-zero. At this instant, you can check. At this instant, Vs and E both are same, na? This instant is pi minus theta. At pi minus theta, Vs and E both are same. So if both are same, so Vs minus E will be 0. Vs minus E 0 means what about the load current? Load current will be 0. So you can check at pi minus theta. We are having, yes, I0 is equal to 0 ampere, right? So that's why here at pi minus theta, it is a 0 ampere. So current is flowing only from alpha to pi minus theta. After pi minus theta till pi, what will happen? From pi minus theta till pi, Vs is less than E, na? So if Vs is less than E, what will happen? Definitely our thyristors will be in a reverse bias mode now. First thing is at pi minus theta, current flowing through thyristor becomes 0, na? And after that, first current flowing through thyristor becomes 0 means first condition for the commutation has reached. And after that, supply voltage is less than the EMF E, right? So due to that, what will happen? Our thyristor will be in a reverse bias mode. Okay. So that's why here, yes, we can write from pi minus theta to pi, T1, T2 will be in an off state. So from, yes, for omega t is equal to pi minus theta to pi minus theta to pi, Vs is less than E. So thyristors T1 and T2 will be again in reverse blocking mode. Reverse blocking mode. Reverse blocking mode. Okay. So now reverse blocking mode. So therefore I0 will be 0 ampere. What about the V0? V0 is equal to E volt. Okay. So I0 0, V0 is E volt. So you can check the waveform. Pi minus theta to pi. This is pi, na? This is pi minus theta. From pi minus theta to pi, V0 is E. I0 is equal to 0. Okay. Next, from pi to pi plus theta. From pi to pi plus theta, what will happen? From pi to pi plus theta, it is like a mod Vs is less than E. So T3, T4, reverse blocking mode. I0, 0, V0, E. Are you getting the point? Okay. I'm saying from pi to pi plus theta, mod Vs is less than E. As mod Vs is less than E, definitely our T3, T4 will be in a reverse bias mode, na? Reverse blocking mode. Okay. So, yes, for omega t is equal to pi plus theta, mod Vs is less than E. So therefore T3 and T4 will be in a reverse blocking mode. Reverse blocking mode. Okay. So if T3, T4 reverse blocking mode, T1, T2 are already in a reverse bias mode. Okay. So whether the current will flow from source to load? No, current will not flow. Okay. So that's why here I0 is equal to 0 ampere, and V0 we are having, it is a E only. V0 is equal to E only. So you can check from pi minus theta, sorry, pi to pi plus theta, pi to pi plus theta, V0 is E, I0 is 0 only. Okay, pi plus theta, right? Pi plus theta means somewhat here, right? So V0 is E and I0 is 0. So pi plus theta to alpha, what will happen? From pi plus theta to alpha, from pi plus theta to alpha, yes, for omega t is equal to pi plus theta to alpha, pi plus theta to alpha. Yes, from pi plus theta to alpha. What is mod Vs? Mod Vs is greater than E. But whether we applied the gate pulse to thyristors T3, T4? No. Pi plus theta to pi plus alpha, sorry. This should be pi plus alpha, right? Okay. So whether we applied the gate pulse to thyristors T3, T4? No. So T3, T4 will be in forward blocking mode. Okay. So T3 and T4 will be in forward blocking mode. Forward blocking mode. Okay. So T3, T4 are in a forward blocking mode, means off state. Okay. So therefore current is not flowing from source to load. So I0 is again 0. And what about the V0? V0 is equal to E. So you can check here. Yes, from this instant till pi plus alpha. From this instant till pi plus alpha, V0 is E and I0 is 0. Now at pi plus alpha, we are going to apply the gate pulse to T3, T4. So once T3, T4 gate pulse is applied, how the current will flow? Yes, it is a minus here plus here. When T3, T4 are turned on at pi plus alpha, current will flow from Vs, T3 load, T4 and again back to the Vs. Na? In this loop, the current is flowing, right? So in this loop, current will flow. So here, can we write V0 is equal to Vs now, right? So V0 is equal to Vs. So from pi plus alpha to 2 pi minus theta for omega t is equal to pi plus alpha to 2 pi minus theta. Mod Vs is greater than E. Mod Vs is greater than E, right? So here it was mod Vs greater than E, but gate pulse not applied. In this case, mod Vs greater than E and we applied the gate pulse. So T3, T4, forward conduction mode. So if T3, T4 are in a conduction mode, so what will happen? V0 is equal to E, Vs only, right? Current is now flowing from source to load, na? So V0 is equal to Vs. And what about the I0? You can check, we are having V0 is equal to I0 into R plus E, na? So therefore I0 is equal to V0 minus E divided by R, which is equal to Vs minus E divided by R, right? So I0 is Vs minus E by R, right? So you can check here. Yes. Yes. For this loop, you can apply KVL. It is a plus Vs minus V0 na, is equal to 0. So V0 is equal to Vs. Next, so you can check V0 is same as the supply voltage. It is a positive, but okay. And I0 is this type of current. Means this same pulse is repeating here from pi plus alpha to 2 pi minus theta. From 2 pi minus theta to 2 pi, what will happen? 2 pi minus theta to 2 pi for omega t is equal to 2 pi minus theta to 2 pi. 2 pi minus theta to 2 pi. Yes, what will happen during this interval? Again, mod Vs is less than E. So thyristors T3 and T4, these two will be in a reverse blocking mode now. Reverse blocking mode. Reverse blocking mode, right? So what is the V0? V0 is equal to E and I0 is equal to 0 ampere, right? I0 0, V0 is E, right? Okay, okay, okay. you can check where the V0 is minus Vs. When T3, T4 conducts, you can apply the KVL to this loop. It is a plus Vs minus V0 is equal to 0, na? So V0 is plus Vs only. Simple apply KVL, right? Next, so here we are getting V0, okay, is equal to Vs. Now you can check here. Now you can check here, right? Okay, so this type of waveform we are getting. So from pi plus alpha till pi minus theta only, we are having a conduction, and similarly from from alpha to pi minus theta we are having a conduction, and pi plus alpha to 2 pi minus theta we are having a conduction. Okay, and after that the same repeats. So this type of waveform we are getting, and you can check from 0 to alpha, none of the thyristor will be in a conduction mode. Alpha to pi minus theta, T1, T2 conducts. Pi minus theta to pi plus alpha, none of the thyristor will be in a conduction mode. Pi plus alpha to 2 pi minus theta, pi plus alpha to 2 pi minus theta, T3, T4 conducts. Is this clear? So this type of circuit operation we are having. Is this clear? Right? So now we are going to derive the expression. So you can check between omega t is equal to 0 to pi, between omega t is equal to 0 to pi, right? Between omega t is equal to 0 to pi, whatever the waveform we are having, V0, the same is repeating from pi to 2 pi. So here periodic angle is pi only. Periodic angle is a pi only, right? So let me write it as V0 average. V0 average. Yes, V0 average is equal to 1 by pi. In that we are having the various intervals na, corresponding to 0 to pi. Yes, we are having the interval like 0 to alpha, alpha to pi minus theta, pi minus theta to pi. Between 0 to alpha, what is the V0? It is a E. Okay, 0 to alpha, V0 is equal to E. E into d omega t. This is 0 to alpha. Plus integration from alpha to pi minus theta. During alpha to pi minus theta, we are having V0 is equal to Vm sin omega t. Same as the supply voltage na, right? So it is alpha to pi minus theta. Yes, it is a Vm into sin of omega t. Next into d omega t. Plus integration from pi minus theta to pi. Pi minus theta to pi. What is the V0? Again, it is a E na. So this is the V0 average, right? Either we can simplify it or keep it as it is. Okay, doesn't matter. So this is the V0 average we are having. Next, what is the I0 average? How generally we write I0 average for RE load? We know na? V0 is equal to I0 into R plus E. Yes or no? V0 is equal to I0 into R plus E. What is the average value of this E? E average is E only na? E average is equal to E only. So therefore, can I write I0 or V0 average? V0 average is equal to I0 average into R plus E average, or it is a E only. So further we can write it as therefore I0 average is equal to V0 average minus E divided by R. Yes or no? I0 average is equal to V0 average minus E by R, right? So either you can first find the V0 average, after that you can find the I0 average, or what we can do from this expression of I0 na, Vs minus E by R, from this waveform also we can find the I0 average, and once we get the I0 average, from that we can find the V0 average also. Okay, in both the ways you will be getting the same answer. Okay, so right, next, so this is the I0 average. Similarly, we can write the V0 RMS. It is same thing, the only change will be same interval will be there. The only thing is e square Vm square sin square of omega t e square and to the power 1 by 2. Okay. So it is V0 RMS 1 by pi into integration from 0 to alpha. It is a e square into d omega t plus integration from alpha to pi minus theta Vm square into sin square of omega t into d omega t plus integration from pi minus theta to pi. It is a e square into d omega t, right? To the power 1 by 2, square root of mean of squared value, right? Next, further can we write I0 RMS? How to write the I0 RMS? Okay, how to write the I0 RMS? Yes. So for that, yes, we need to consider this waveform. So you can check for I0 over 0 to pi, whatever the I0 waveform we're having, the same is repeating from pi to 2 pi. So can I write 1 by pi integration from alpha to pi minus theta only? Okay. So let me write it as 1 by pi integration from alpha to pi minus theta. During this interval, what is the I0? It is a Vs minus E, na? Right? So let me write it as Vs means Vm into sine of omega t minus E divided by R to the square, na? Into d omega t to the power 1 by 2, right? To the power 1 by 2, right? So in this way, we can find the I0 RMS. I0 RMS. Okay. So it is a further we can simplify it. Take the r square outside, this divided by pi outside, and we can square this bracket. Okay, as a minus b bracket square, a square, right, minus twice ab plus b square, in that way. Okay, so no need to simplify here. At the time of numericals, we will discuss it. Okay, because at the time of numericals also, we are not going to use the expressions directly. We need to write their expression. We need to simplify there. Okay, we need to derive the expressions at the time of solution, because we cannot memorize this these many number of expressions, right? Okay, so this is your I0 RMS. Next, what is the load power? P0 average load power. Yes, can anyone? We are having RE load. So how to find the P0 average? We have discussed this thing. If load is resistive, it is a V0 it is a I0 RMS square into R, right? If load is a RE load, it is a combination of R and E. So how to find P0 average? Power consumed by the resistor plus power consumed by the EMF, right? What is the average power consumed by the resistor? It is the I0 RMS square into R plus what is the average power consumed by the EMF? It is the E into I0 average. You can multiply the I0 and E. Okay, you will be getting the power of the E, and E is a constant, na? So if you take, right, suppose I want to find the power consumed by E. Power consumed by E. Only E I am writing, only E is equal to, how we can find? It is equal to 1 by pi integration from, we are having the, if you check this expression, waveform, we are having I0 is flowing from only alpha to pi minus theta. Okay, so it is like a alpha to pi minus theta. It is like a alpha to pi minus theta. Yes, it is a E into I0 into d omega t. Na? And what is I0 value? It is a 1 by pi integration from alpha to pi minus theta E into, what is the I0? I0 is your Vs minus E by R. So it is a Vs minus E by R into d omega t. So further we can write it as E is a constant, so we can take it outside. So E into this bracket, na, it is like 1 by pi integration from alpha to pi minus theta, and this term, it is a Vs minus E divided by R into d omega t. So you can check here what this term indicates, this bracket, what this bracket indicates. Yes, this bracket is I0 average only, na? You can check I0 average. Suppose I want to write the I0 average. How we can write the I0 average? It is like 1 by pi integration 1 by pi integration from alpha to pi minus theta, this term into d omega t, and that is what I have written here, right? So this is your I0 average. Is this clear? So that's why power conserved by the E is E into I0 average, right? E into I0 average, right? So E into I0. And what is the power conserved by the resistor? That thing we already discussed during the chapter number 1, as well as during the starting of the chapter number 2. Okay, in the half wave control rectifier with a purely resistive load, there we derive the expression. Okay, so it is I0 RMS square into R plus E into I0 average. Okay, E into I0 average, right? Next, because I have taken only this interval. Why? Because you can check here this waveform. E is variable constant na. If I multiply this E, red line, and this I0 waveform, if I multiply this E, and if that I0, what is the multiplication waveform? E into I0. So during 0 to alpha, what is the E into I0? It is a 0 only na. During alpha to pi minus theta, what is the E into I0? It is a non-zero. And pi minus theta till pi, what is the E into I0? It is a 0 into this E, so again 0. So we are having the PE waveform, that is a power consumed by the EMF waveform, will be non-zero only from alpha to pi minus theta. So I have taken the interval only from alpha to pi minus theta. It is same method of your I0 interval, right? So this is the power consumed by the EMF E, right? Power consumed by the EMF E. Is this clear, right? Now, how will the waveform for the source current? IS waveform. Zero to alpha, alpha to pi minus theta, pi minus theta to pi, pi to pi plus alpha, pi plus alpha to 2 pi minus theta, and 2 pi minus theta to 2 pi. Come on, tell me the IS waveform. Bridge configuration we are having. In the bridge configuration or the bridge rectifier, when T1, T2 conducts, IS is same as that of I0 or minus I0? In a rectifier, in a bridge rectifier, when T1, T2 conducts, IS will be same as that of I0, or it is a minus I0? Yes, it is the same as that of the I0 na? When T1, T2 conducts, I am saying, when T1, T2 conducts, I am saying, okay, it is the same as that of the I0 na? So you can check I0 we are having from alpha to pi minus theta only non-zero. So therefore in the IS will be getting this pulse. 0 to alpha it is 0, and alpha to pi minus theta, this type of waveform. Pi minus theta to pi, again it is 0. So this value is like your Vs minus E divided by R. Pi to pi plus alpha, none of the thyristor will be on state again. So IS is again 0. Pi plus alpha to 2 pi minus theta, what is IS? Pi plus alpha to 2 pi minus theta, what is IS? Whether it is a plus I0 or minus I0? Minus I0, why? Because T3, T4 conducts na. So therefore it is a negative here. And here it is a 0, right? So we'll be getting this type of waveform, right? For source current, for the source current, right? It is a Vs minus E by R. Okay, Vs minus E by R. Is this clear? Now we are having I0 waveform like this. Omega t 0 alpha pi minus theta, pi plus alpha, and 2 pi minus theta. And last one is the 2 pi, right? Yes. So I0 waveform, we know, we have discussed it is like this. Now my question is whether the RMS value of the source current and RMS value of the load current both will be same or different. RMS value of source current and RMS value of load current both will be same or different. Yes, both will be same only na, right? Both will be same, right? So IS RMS is equal to I0 RMS. RMS is equal to I0 RMS. Right. Next, what is the conduction time of each thyristor? Conduction time of each thyristor. Come on. What is the conduction time of each thyristor? Thyristor T1, T2 will be in a conduction mode from omega T is equal to alpha to pi minus theta. Na? So it is like from pi minus theta minus alpha divided by omega. So it is equal to pi minus theta minus alpha divided by omega. Pi minus theta minus alpha divided by omega. Right? Is this clear? Okay. Okay. So this is about the RE load. Okay. RE load. Next, let us discuss the RLE load. RLE load. Yes. Single phase fully controlled bridge rectifier. Okay. Bridge rectifier. With the RE load. Sorry, RLE load. RLE load. So circuit diagram. VS T1, T2, T3 and T4. Okay. So RLE. This is a V0 and here it is a I0, right? V0 and I0. So here, yes. In this, we are going to discuss the cases like if L is having a high value. Second is if L is a low value. Okay. Then what will happen? Vs is equal to Vm into sine of omega t. This is a E. Ig. Right. So we're going to apply the gate pulse. Yes. Here it is a Ig1, Ig2, Ig3, Ig4. Again Ig1, Ig2. Let us first discuss for high value of inductor. Okay. if inductor value is high, then in the output voltage, the effect of EMF E will not be observed. Okay. Right. So it is like, yes, from here to here, yes, we are having thyristors T1, T2 conducts. From here to here, T3, T4. Okay, so yes, I'm saying if the value of inductor is high, then in the output voltage, the effect of E will not be observed, right? Or in the circuit operation, the effect of E, right? EMF E will not be present. Are you getting the point? Means this waveform is similar to that of your RL load with a high value of inductor. Yes or no? Please note it, right? This is very important. Okay. So I'm repeating it. If the value of inductor is high, because the thing is what is happening in this circuit, you can check from omega t is equal to alpha, from omega t is equal to alpha till theta. Okay, let us consider till theta. Inductor is storing the energy, and from theta till pi plus alpha, inductor is releasing the energy. Yes, from theta to pi, it will release the energy in opposition to that of the EMF, and from pi to pi plus alpha, it will release the energy in opposite to that of the EMF as well as supply voltage, right? So that's why in the output voltage, the effect of E will not be observed. I am saying this is only when value of inductor is high. So generally in electric motor case, okay, we are having a windings, na? Large number of turns we are having armature winding. Okay, you can check large number of turns we are having. Okay, and as we know in the case of inductor, yes, we are having, if the number of turns are more, definitely your inductor value will be more, right? So that's why we are having generally the high value of the inductor. So that's why we'll be getting this type of waveform, right? Let me write this circuit operation during different intervals. Okay, during different intervals, right? So it is like till theta. Theta means somewhat here. Okay, this is theta, or let me write it as a theta 1. This we consider it as a theta na. So this is like a theta 1. Okay, and the pi minus theta 1 means this instant. This is your pi minus theta 1. Okay, so I'm writing circuit operation for omega t is equal to alpha to theta 1, T1 and T2 conducts, because we are applying the gate pulse na. So T1, T2 starts conducting. Inductor L stores energy. So you can check here during in this circuit, when T1, T2 are in on state, supply voltage is positive. T1, T2 are in on state, current will be flowing from Vs T1 load T2 and again back to the Vs. So during this, V0 is equal to Vs. Okay, inductor is just storing the energy. Okay, so V0 is equal to Vs. Inductor is storing the energy, and as value of inductor is high, so therefore your I0 is equal to capital I0. I0 is equal to capital I0. Right?
Hello.
Yes.
Sir, in the previous case, what is the PIV rating of the thyristor actually?
We'll discuss it during the numericals. Okay.
Okay.
In the booklet, we're having some numericals. At that time, we'll discuss it. Okay.
Okay.
Right. Okay. Yes. So I0 is equal to capital I0. I0 is equal to capital I0. So you can check here. Yes. During alpha to theta 1. Yes, we have written theta 1. Let me write it as a
Okay.
Yes. Okay. So for omega t is equal to alpha to theta 1, Yes, it is like T1, T2 are in on state, inductor go on storing the energy. Okay, so V0 is equal to Vs only. V0 is equal to Vs. V0 is Vs, I0 is equal to capital I0. Next, from theta 1 till pi, what will happen? From theta 1 till pi, let us discuss what will happen. For omega t is equal to theta 1 to pi. So from theta 1 to pi, our inductor go on releasing the energy through thyristors T1, T2 only, right? Because at theta 1, what is happening? At theta 1, it is like inductor voltage is a 0. Means supply voltage is equal to VR plus E. At theta 1, it is like a supply voltage is equal to VR plus E. Means inductor voltage will be 0. Okay. So after theta 1, our inductor voltage will be negative. Means inductor starts releasing the energy. So from theta 1 to pi, when inductor releases the energy, your inductor energy and supply energy both will be adding. But EMF energy will be opposing. EMF energy will be opposite. Okay. So let me write here. Yes. Inductor releases energy. Inductor releases energy from theta 1 to pi. From theta 1 to pi, inductor releases energy. Okay. So again, what is the V0? V0 is equal to Vs only. And I0 is your constant current. Okay. I0 is a constant current. So theta 1 to pi also you can check V0. It is same as that of the supply voltage. Next, after pi, what will happen? Supply voltage polarity is reversed. Supply voltage polarity is reversed, means minus here plus here. So now inductor will release the energy in opposition to that of EMF and the supply voltage. Are you getting the point? Okay. So from theta 1 to pi, it is like inductor was releasing the energy, and to the inductor energy, supply energy was assisting. After pi, what will happen? Inductor will release the energy, and in opposition to that of the EMF and a Vs. But you might be thinking that how the inductor can release the energy in opposition to that of the supply voltage and E. You can check nearer to the pi, what is the value of supply voltage? Supply voltage value is very less now nearer to the pi, right? So therefore supply energy also less, right? And inductor we considered here is a high value. Inductor we considered here is a high value. So from pi to pi plus alpha also, inductor releases the energy, and T1, T2 will be in a conduction mode. T1, T2 will be in a conduction mode. So for omega t is equal to pi plus alpha, inductor releases energy. Okay, releases energy. So again V0 is equal to your minus Vs now. V0 is negative now. You can apply KVL to this loop, you will understand. Plus Vs minus V0 is equal to 0, right? Sorry, T1, T2 conduction, right? So it is minus Vs minus V0 is equal to 0 now. So V0 is equal to minus Vs. Okay. So therefore it is a negative. V0 is minus Vs. So you can check the waveform. During this interval, V0 is a negative, right? And I0 is a constant. At pi plus alpha, again T3, T4 were turning on. So from pi plus alpha till pi plus theta 1. Okay, from pi plus alpha till pi plus theta 1. Again, inductor stores energy. Okay, so yes, here. So for omega t is equal to pi plus alpha to pi plus theta 1. T3, T4 conducts. Inductor stores energy. Okay, so what is the V0? You can check. V0 is equal to Vs. So now when T3, T4 conducts, apply KVL. Plus Vs minus V0 is equal to 0 now. So plus Vs minus V0 is 0, means V0 is equal to Vs. Okay, so V0 is equal to Vs, right? So this is still pi plus theta 1. From pi plus theta 1 to 2 pi. From pi plus theta 1 to 2 pi, what will happen? For omega t.
Pi plus alpha to.
Yes.
T3, T4 conducts.
Pi plus theta 1 to 2 pi. Again T3, T4 conducts.
T3, T4 conducts.
And inductor releases energy. So again, what is V0? V0 is equal to Vs only, right? T3, T4 are in on state, inductor is releasing the energy. But in this case, you can check when T3, T4 conducts and when inductor releases the energy, na? So supply energy and inductor energy both will be adding here. Okay. And after 2 pi, what will happen from 2 pi to 2 pi plus alpha? Supply voltage is positive. Inductor continuously releasing the energy, and supply energy and E will be now adding, and inductor energy will be less. Inductor energy will be opposing. Okay. But we are having a high value of inductor. Due to that, yes, inductor will successfully release the energy till 2 pi plus alpha. Okay. So from 2 pi, from omega t is equal to 2 pi to 2 pi plus alpha. Yes, it is like inductor releases energy through T3, T4. Through, it is T3, T4 are in conduction mode. Okay. So what is V0 during this interval? You can check during this interval. Supply voltage is a positive now. This is a plus here, minus here. And when T3, T4 conducts, yes, how the current is flowing? Inductor is releasing the energy, na? So like this, the current is flowing. Inductor is releasing the energy. So now what is the V0? You can apply KVL here. Minus V0 minus Vs is equal to 0, na? So what is V0? V0 is minus Vs. Okay. So V0 is equal to minus Vs. V0 is equal to minus Vs. Right? So you can check the waveform. We are having V0 is a minus Vs. V0 is equal to
2 pi to 2 pi plus alpha.
Okay, right? So 2 pi to 2 pi plus alpha, V0 is a negative here, right? So this is the overall circuit operation. Means you can check here, even though the EMF is present in the circuit, but the effect of EMF is not, we will not observe the effect of EMF during the circuit operation because due to the inductor here, due to the inductor, right? So can we say that this is similar to that of your RL load? Yes or no? Whether it is similar to that of the RL load? Yes, RL load with high value of inductor. Same here. Okay, same. So let me write here. Yes. Circuit operation for RLE load. RLE load with the high inductance, high L inductance, okay, is similar to that of RL load with the high inductance, high value inductor, right? This is very important. Is this clear? Now, yes, what is the V0 average? What is the V0 average here? You can check from alpha to pi plus alpha, or from 0 to pi, whatever the waveform we're having, the same is repeating. Okay, so you can write V0 average is equal to 1 by pi integration from alpha to pi plus alpha Vm into sine of omega t into d omega t, right? So if you simplify it, we'll be getting it as 2 Vm by pi into cos alpha. This is the V0 average. Yes or no? What is the I0 average? I0 average, come on. We are having RLE load. How to find the I0 average? Yes. What is the I0 average? Whether it is same as that of the RL load or different. Yes. Shweta, you are given V0 average minus E by R. Very good. Correct. Yes, you can write I0 average is equal to what? V0 average minus E divided by R again, which is equal to, you can check the I0 waveform. It is a constant, na? So can I say that I0 average is a constant, capital I0, right? So it is equal to capital I0. What is I0 RMS? I0 RMS, whether it is equal to capital I0 only, because we are having I0 waveform is a constant, na? So what is the I0 RMS? It is a constant. That is whatever the magnitude of the I0, na, that will be your I0 RMS. That will be your I0 average also. Okay. So let me write it as I0 RMS is equal to capital I0. I0 average is equal to I0 only. Okay. So therefore, can we write it as? Yes. In this case, I0 RMS is equal to I0 average, which is equal to V0 average minus E divided by R, which is equal to capital I0, right? This relation is very important. Okay. So if we are having a highly inductive load, average value of the load current is equal to RMS value of the load current, which is equal to capital I0, which is equal to V0 average minus E by R, because average value of inductor is 0, na? So that's why load voltage average value is equal to VR average plus E, right? So from that we can find I0 average. Okay. So it is equal to V0 average minus E by R. Similarly, we can find V0 RMS. Yes, you can check it is a 1 by, we are having pi integration from alpha to pi plus alpha. It is a Vm square into sine square of omega t into d omega t to the power 1 by 2, to the power 1 by 2. So we can write it as, if we simplify it, we'll be getting it as a Vm by root 2, which is equal to Vs RMS. Because we are having V0 means continuously non-zero waveform, na? If you simplify this, we'll be getting it as a Vs RMS only, right? This is a V0 RMS. Now we are having a RLE load. We are having a RLE load. So can we find the P0 average? P0 average here. Yes. Can anyone? What will be the P0 average? What is the power consumed by the inductor? Power consumed by the inductor is 0, right? Power consumed by the inductor is 0, correct? So now we are having, if we remove the inductor, we are having only resistor and the EMF E. What is the power consumed by the resistor? It is I0 RMS square, okay, into R plus E into I0 average, right? E is a constant voltage, okay? So its the power will be equal to E into I0 average. Or further, you can write it as I0 RMS means again capital I0, na? So it is a capital I0 square into R plus E into capital I0. Okay, in this way also we can write. So this is the P0 average, right? P0 average. Next, conduction time of each thyristor. Conduction time of each thyristor. Yes. If you check thyristor T1, T2 are in a conduction mode from alpha to pi plus alpha, na? So it is a pi plus alpha minus alpha divided by omega. So it is a pi by omega. This is a conduction time of each thyristor. Okay, that is a pi by omega, right? Is this clear? Similarly, you can write the peak inverse voltage. In this case, the PIV rating will be equal to what? At a time, two thyristors will be in a conduction mode, na? Right? So your PIV rating will be equal to Vmax. Okay, you can write it PIV rating is equal to Vmax. Otherwise, we can discuss it while discussing the numericals also, right? So yes, so this is about the circuit operation, okay, for RLE load, but highly inductive load, Now suppose if the value of inductor is reduced, then what will happen? That is nothing but, let us consider the discontinuous conduction. Okay, so discontinuous conduction. Next, so let me write RLE load, and conduction is a discontinuous. Discontinuous conduction. Yes. Same circuit diagram. I will directly draw the waveforms here. Okay. Yes. Right. So this magnitude is like a E. This is a E. And here we'll be getting this as a Vs. So now for discontinuous conduction, you can observe the V0 waveform. It is a combination of supply voltage and the EMF, right? Means what? During beta to pi plus alpha, when all the four thyristors will be in off state, na? At that time, V0 is E only. Yes or no? Right? So, and how will the I0? I0 will be like this. From alpha to theta, it is like increasing, and next it is still beta, it is decreasing. It will be 0 in between, and next again increases, again decreases, like this, and again, right? So we'll be getting this type of I0, right? You can check here. In circuit operation from alpha to theta 1, it is the same as that of whatever we discussed earlier. From theta 1 to pi, inductor releases energy, same as that of your previous one. But in the previous case, it was like from pi to pi plus alpha, inductor was releasing, na? But here it is like inductor releases energy through T1, T2 from pi to beta only. At beta, it is like inductor energy is less than that of your supply energy and EMF energy. So that's why if inductor energy is less than the supply energy and your EMF energy, so it is like your all the four thyristors will be in the off state. So that's why V0 will be equal to only E. So this is the only change we are having. Are you getting the point? So you can check the circuit. Yes, here we are having a circuit. No, this is RE load. Yes, here it is RLE load. Means what is happening for discontinuous conduction from alpha till theta 1, I am saying from alpha till theta 1. Theta 1 means we consider this point. Na? So from alpha till theta 1, T1, T2 are in a conduction mode. Current will be flowing from Vs, T1 load and again back to the T2 through this loop. So V0 is Vs only till theta 1. Theta 1 to pi, inductor releases energy through T1, T2. V0 is Vs. Pi to beta. Now in the previous case, it was like from pi to pi plus alpha, na, inductor was releasing the energy. But in this case, as the value of inductor is less, due to that, inductor energy stored is also less, right? So due to that, inductor was not releasing the energy till pi plus alpha. Inductor will releasing the energy till beta only. Okay, till beta only. Okay, so that's why, and that beta is your less than pi plus alpha, na? Beta is less than pi plus alpha. So only till beta, inductor releases the energy through T1, T2. So V0 is equal to Vs. And from beta to pi plus alpha, what will happen? It is like inductor energy is less than that of, yes, energy of the EMF and the supply. Because you can check after pi supply voltage is negative, na? So supply energy and E both will be adding. So inductor is less. So due to that, inductor energy is less than that of EMF energy and supply energy. So that's why our thyristors T1, T2 will turn off. And yet we have not applied the gate signal to thyristor T3, T4 also. Okay, so that's why during beta to pi plus alpha, all the four thyristors will be in a off state only. So that's why your V0 is equal to E only, right? V0 is equal to E. So that's why we're getting this type of waveform. We're getting this type of waveform. Is this clear? So this is for discontinuous conduction, means if the value of inductor is less, okay? But most of the times, if you check the previous questions, they have asked the questions based on continuous conduction only, and that too by considering the constant load current, right? So this is about for RLE load. So in the single phase fully controlled bridge rectifier, we discussed the R load, RL load, RL with freewheeling diode, RE load, and RLE load. Please go through it. These 5 loads are very important. And the V0 waveform and I0 waveform, whatever we discussed, for this configuration, that is for bridge configuration, the same will be appearing for your midpoint tapped or center tapped transformer configuration also, right? Operations are same. In the fully controlled, we're having 4 thyristors. In the center tapped, we're having 2 thyristors only. Okay. The only change is conduction of the devices. Let me indicate here the devices which will be in a conduction mode. Yes, from here to beta, alpha to beta, T1, T2 conducts, beta to pi plus alpha, none of the switch will be on state from beta to pi plus alpha. Please listen it carefully. No switch conducts, okay? No switch conducts. And from pi plus alpha to this instant, that is like pi plus beta. This instant is like pi plus beta. It is like a T3, T4 conducts. And again, none of the switch will be in on state, right? No switch conducts. No switch conducts. Is this clear? Right? So for RLE load, continuous conduction and discontinuous conduction. For RL also, we discussed the continuous and discontinuous conduction. Okay. Yes. Now next one we are going to discuss. Yes, we're having the time. Yes. So next we are going to discuss the same RLE load, but the inverter mode of operation. Right? Please listen it. They have asked the question in one of the examination. Yes. Inverter mode of operation. Single phase, fully controlled bridge rectifier RLE load, but in that we are going to discuss the inverter mode of operation. Inverter mode. Same circuit diagram as that of the previous case. We are discussing the inverter mode of operation. So that's why I have reversed the polarities of the EMF E. Supply voltage Vs, thyristors are T1, T2, T3, T4. Okay, let me draw the waveform. Yes, for RLE load. Actually, for inverter mode of operation, the inverter mode of operation means, first let us understand. If you check, we're having the 2 circuitries. One is a rectifier. The rectifier is a circuitry where input is AC, output is DC. Rectifier transfers power from AC source to the DC load. Yes or no? Second thing, inverter. In the inverter, it is opposite. Input is DC, output is AC. Okay. Now we can use this rectifier circuitry as an inverter. We can use this rectifier circuitry as an inverter. So for that, yes, it is like power should flow from DC side to AC side, na? Then and only then we can say that our circuitry is operating as an inverter. Please listen. In the rectifier, we're having the input is AC, output is DC. Rectifier transfers the power from AC side to DC side. Inverter circuitry, input is a DC, output is AC, right? So inverter circuitry, yes, it is like power is transferring from DC side to AC side. Now in this circuit, at one side we're having a AC, at one side we're having a AC, at second side we're having a DC, right? It is like a rectifier and input is AC, output is a DC. Now, if I select alpha greater than 90 degree, if I select alpha greater than 90 degree, and if we reverse the polarity of E, if we reverse the polarity of E, you can check for a RLE load, continuous conduction mode. Okay, if I keep alpha greater than 90 degree, and if we reverse the polarity of the E, then it is like our power will be transferring from DC side to the AC side. How it will transfer, we will discuss. You can check for continuous conduction. For continuous conduction, whatever the V0 we are having, what is the V0 we are having? From alpha to pi plus alpha, it is same as that of the supply voltage. Alpha to pi positive, pi to pi plus alpha negative. Pi plus alpha to 2 pi positive, 2 pi to 2 pi plus alpha again negative. And we have derived the V0 average expression also. What is the V0 average expression? It is a 2 Vm by pi into cos alpha. Means can we say that V0 average is proportional to cosine of alpha? And if I select alpha greater than 90 degree, so what is the V0 average, which is proportional to cos alpha? So it is cos greater than 90 degree. What is the value of cos greater than 90 degree? Cos greater than 90 degree is negative, na? So here your output voltage is negative. The meaning is your output power is also negative. Now output power is negative. The meaning is output power is negative means what? It is like a load is supplying the power, na? Load consumes the power at that time. It is like power is positive. Output power is negative means what? It is like a load is supplying the power. Now load supplying the power means what? The power is flowing from DC side to the AC side. Are you getting the point? Okay. So two basic things are required in order to operate a single phase fully controlled bridge rectifier. Okay, in inverter mode. And now important thing, this inverter mode of operation is possible only in the case of RLE load. For that also we are having the two specific requirements. One is the alpha greater than 90 degree and second one is the E should be reversed. E should be reversed. In a drive, you might have heard about the regenerative braking. Braking means what? It is like your power is moving from or the circulating from load to the source, from load to the source. Na? So in the regenerative braking, we are using this concept. Okay, so let us discuss how it works. So alpha greater than 90 degree. So let me draw the waveforms first. Alpha greater than 90 degree. This is a Vs. Again, we are going to discuss the continuous conduction only, right? So pi, 2 pi and 3 pi. E is there, but the effect of E will not be observed due to the high value of inductor. Okay, so let me draw the V0 and I0 waveform. If alpha is greater than 90 degree means this is 90 degree, na? We are supposed to apply the get pulse to thyristor T1, T2 at this instant. Okay, T3, T4 let us suppose at this instant. Okay, and similarly T1, T2 at this instant. Okay, So we are applying the gate pulse to T1, T2 here, T3, T4 here, and T1, T2 here. Okay. So for continuous conduction, yes, our V0 waveform will be like this. Please be careful. I have selected alpha greater than 90 degree. That's why we're getting this type of waveform. Right? So it is like, let me indicate this as a alpha. This is a pi. This is like a pi plus alpha. Pi plus alpha. This is like a 2 pi. Here it is a 2 pi plus alpha. Okay. And this is like a 3 pi. Right? I0 is a constant current only. So how is the conduction of the devices? Yes, let us check. From alpha to pi plus alpha, T1, T2 conducts. Alpha to pi plus alpha. T1, T2 conducts. From pi plus alpha to 2 pi plus alpha, T3, T4 conducts. Right? Now you can check if alpha is greater than 90 degree. If alpha is greater than 90 degree, it is like alpha should be greater than this point. Na? So that's how I selected here. Now, please listen the circuit operation. Okay. Here I have connected E as a reverse voltage. E is a reverse voltage here we have connected. Okay. So next, let us consider at omega t is equal to alpha, we have applied the gate pulse to the thyristor T1, T2. So what will happen? Yes. In this circuit, suppose at omega t is equal to alpha, that is Vs is positive, and we have applied the gate pulse to thyristor T1, T2. So it is like current will flow from Vs, T1, load T2, and again back to the Vs. Na? In this loop, the current will flow. Yes or no? Inductor go on storing the energy. But inductor will store the energy. Inductor will store the energy only till pi. Inductor will store energy only till pi. Means for very short interval, the inductor is storing the energy. After pi, what will happen? After pi, you can check supply voltage will be negative. Even though the supply voltage is negative, but inductor will go on releasing the energy, and here EMF E is also there, na? E and inductor energy both will be adding. So due to that, the resultant current will flow from LET2 in opposition to that of the supply voltage T1 and again back to the load. In this loop, the current will flow. So you can check from alpha to pi, T1, T2 are in a conduction mode. Inductor was storing the energy. From pi, okay, from pi till pi plus alpha, inductor is releasing the energy, and at the same time, E is also there. So inductor energy and E energy both will be adding, na? So that's why here our resultant conduction will be from through T1, T2 only. So you can check when T1, T2 conducts after pi, okay, supply voltage is negative and current is flowing like this through T1, T2 and in opposite to the supply voltage. So what is the V0 here? You can check or apply KVL to this loop. It is a minus V0. It is a plus minus Vs is equal to 0. No? Minus V0 minus Vs is equal to 0. Minus V0 minus Vs is 0 means what? V0 is equal to minus Vs. That is a V0 is negative. So you can check the waveform. After pi, we have V0 is negative. The meaning is here definitely your V0 is negative. But what about the I0? I0 is a positive only because current flowing through the load is still in the downward direction, na? Right? So I0 is a positive only. Next, at pi plus alpha, we are going to apply the gate pulse to T3, T4. So at pi plus alpha, when T3, T4 are turned on, current will flow from Vs, T3, load T4, and again back to the Vs. In this loop, the current will flow, right? So if the current is flowing into this loop, what is I0 again? I0 is in downward direction only. So I0 is positive only. So what is a V0? You can check here. KVL to this loop, it is a minus V0 plus Vs is equal to 0 now. Minus V0 plus Vs is equal to 0 means V0 is a Vs. Okay, so you can check. During this interval, pi plus alpha 2 pi, V0 is equal to positive. After that, again, what will happen? Yes, after 2 pi, supply voltage is positive. So polarity will be plus here and minus here. So now inductor will go on releasing the energy. And to the inductor energy, EMF energy will be getting added. So that's why again T3, T4, again your T3, T4 will be in a conduction mode. Okay, so you'll be getting this type of waveform. Now, if you derive the V0 average expression, yes, it will be similar to that of whatever we derived earlier. V0 average is equal to what? It is like a, you can check here. Now I am considering it as 1 by pi, because whatever the waveform we have from 0 to pi, the same is repeating from pi to 2 pi. Okay, so it is a 1 by pi integration from alpha to pi plus alpha. 1 by pi integration from alpha to pi plus alpha. During this interval, what is the V0? V0 is same as that of the supply voltage only. Supply voltage negative, this is also negative. Supply voltage positive, this is also positive. Okay, so it is a Vm into sine of omega t into d omega t. So you can check here, which is equal to 2 Vm by pi into cos alpha. This is your V0 average. So as alpha is greater than 90 degree, as alpha is greater than 90 degree, so therefore V0 average is equal to what? It is a negative, no? V0 average is equal to, V0 average is negative. So if your V0 average is negative, what is your load power? You can check, load is constant here. Load current is constant. So load power is equal to V0 average into I0. So V0 average is negative means load power will be your negative. Is this clear? So load power is negative means it is like power is, load is supplying to the source. Load is supplying to the source. That is nothing but your inverter mode of operation. Okay, inverter mode of operation, right? They ask the questions. For the inverter mode of operation, E should be reverse and alpha should be greater than 90 degree. Alpha should be greater than 90 degree, right? Then and only then it is possible, right? Okay. So TK will stop here. If you are having doubts, please ask. Tomorrow we will discuss about single phase half controlled rectifiers. Okay, half controlled means just like a 4 switches only, but the controlled switches, uncontrolled switches. After that, we will discuss the numerals and input power factor expression. Right, input power factor expression is very important for REL load and REL-E load. Okay, yes.
Sir, 11F, sir.
Yes, 11
F.
Just a minute.
Hello, sir.
Yeah, just a minute.
F.
Yes.
Sir, before page, sir, the TC conduction time.
Before
page, sir, conduction time TC.
Okay, this one.
You write VM. That's
okay. No, this is actually PIV I wrote. Okay.
Oh, okay.
TC.
Sir,
Yes.
And another doubt.
How the time will be in voltage, right?
Yeah, that's one. And another doubt in 2F,
Just
sir.
a minute. Let me write here. TC will be like your pi minus alpha by omega, right? And in the previous page, PIV we wrote PM. Okay, it is fine. Yes.
2F, sir.
2F.
Yes, sir.
Yes.
Sir, that waveform I naught equal to minus IS, you wrote one equation, sir. Sir, here, sir, here, I naught equal to minus IS, source current will be negative.
Yes. Here it is. Not here. Here it is. Yes.
Sir, here for source current, output current is negative, sir, but in the graph, output current is positive, sir. How to relate that, sir?
but in the graph output current is positive. Okay, listen, output current is always positive.
Okay,
But
sir.
if I0 is positive, what about the IS? IS will be negative, na?
But same current around flowing, no, sir. What the current IS is flowing, that only flowing through the load also. From the IS current around flowing through the load also, then how it can be negative, sir? If it is
No,
negative,
you
means
can
load
check-
current
you
also.
can check. You can check the direction of the current, na? How the current is flowing? VS, T3, load, T4, and VS, na? You can check the current is flowing from VS, T3, load. In the load, the direction of current is downward, na?
Okay, sir.
Next, the same downward current will come here. It will be flowing through the T4.
Okay, sir.
Same current will come here, same current here, same current here. But in this branch, what is the direction of the current? Downward.
Yes, sir.
We consider the IS is positive, means upward direction.
Okay, sir.
Actually, current is flowing in downward direction, so it will be negative. Right?
So this equation resembles that source current is negative, but the load current is positive.
Yes, Lord, always keep it in mind in rectifiers. In rectifiers, we don't have the negative current at all. You can check any load. You can check any load. Because
Okay,
we are having the
sir.
switches, we are having the switches. These switches are not allowing the reverse current, na?
Yeah, yes, sir.
So
Sir,
that's why in rectifier you can check. Definitely in rectifier, your load might be the negative for some interval, but your load current is always positive.
sir, and another doubt, sir. Usually, generally, you say that when VL is negative, inductor start to discharge, sir. I mean, inductor releases the energy, sir.
Yes.
Inductor usually will release energy for the opposition, for sudden change, to show the opposition, sir. How these two things will be related, sir? VL negative means it will be releasing the energy. What's the opposition there, sir?
Okay. Just a minute. Let me tell you. Yes. Your doubt is when VL is negative,
Inductor is releasing the energy.
inductor releases energy. Yes. Huh.
How to relate these two, sir? Because inductor will release the energy only when there is a sudden change. For that opposition alone, it will release the energy to show the opposition for sudden change. How these two will be related, sir?
Okay. Let me state. VL is equal to what? L into DIL by dt.
Yes, sir.
So VL positive means DIL by dt is positive.
Yes, sir.
Now VL negative means DIL by dt is negative.
Okay, sir.
So if DIL by dt is negative means your current is decreasing.
Oh,
It is like
Okay.
this increasing and it is like this decreasing. So till this instant, it is like storing energy. And
Yes,
after this, it is like releasing energy.
so here current changing from positive to, that means the slope is changing from positive to negative. So that's the sudden change.
Slope is negative. Huh?
So that's the sudden change experienced by the inductor, sir.
This is not the sudden. This is sudden change opposed. Suppose if
Then what is the sudden change, sir? It is the opposition, means what is the sudden change?
I will tell you. Suppose we are having the circuit like, let us consider simple circuit. We have discussed, na? Supply, and here let me write it as a R and L. Okay.
Yes, sir.
So this is VS plus minus. Okay, VS positive is then plus here minus here. Okay. R and L. In this case, without inductor, how is the load current we are having?
It will be in phase, sir.
Yes, it will be like alpha to pi. It is like this.
Pi.
Na? Yes or no?
Alpha. Yes, sir.
And after that till 2 pi, it is again 0. Okay, this is our
Yes, sir.
I0. In case of inductor, this is your omega t. Here it is omega t, right? So
Yes,
in
sir.
case of inductor, how is the load current?
It will be till beta.
It is increasing, na?
Yes, sir.
So we consider that till this instant on just before 2 pi. Let us consider it as theta. Okay.
Yes, sir.
Inductor is storing the energy, and after that we say that inductor releases the energy.
Okay, sir.
Suppose if inductor is not opposing, means suppose if inductor is not releasing the energy, then
Okay,
what
sir.
will happen? After pi, you can check supply voltage is reversed, means minus here plus here, na? So
Yes,
it is
sir.
like supply voltage will try to circulate current in the opposite direction. But whether our inductor will allow the whether our thyristor will allow the reverse current? No.
No, sir.
So sudden change means what? Suppose if inductor is not opposing the change in the current, na, then it is like at pi, current will suddenly decrease to 0, suddenly fall to 0.
Okay, sir.
Due to the presence of inductor, what is happening? Our current is whether it is suddenly decreasing?
No, sir.
It is slowly decreasing, na?
Showing the opposition.
That
Yes,
is
sir.
also showing opposition, right?
Sir, in inverter operation, I have one doubt, sir. In inverter operation, we have taken source as an input, sir, but you said DC will be the input, sir.
No. Actually, source is this one, AC side only.
Okay, sir.
In the inverter, actually, the thing is, what is happening? Current is flowing, power is flowing from this side to this side, na?
Yes, sir.
So generally, in electrical circuit, we are having the concept like the element to which is supplying the power. That is nothing but the source.
Yes, sir. Sir,
So
this concept.
Yes.
This concept is applicable for regenerative braking, sir. But how it can be called as inverter, sir? Because in inverter means it should be DC to AC.
So
But
what
here,
this is what happening, na? Power is actually flowing from DC to the AC. This
But
side
at-
we're having AC, this side we're having AC, yes or no?
yes, sir.
And power is flowing from this side, DC. This side is DC, that is the load side of the rectifier.
But we are utilizing the VS only, no, sir, for the operation. Then how we can call it, sir?
What, where?
We are utilizing. We are utilizing the power from voltage. Then only we are giving back, no, sir. Then how it can be called as inverter mode, sir?
No. The inverter mode of operation, the thing is like power is you are transferring from DC side to AC side. That's it.
Oh.
It is not like your DC to AC conversion.
Okay, sir.
Getting
I
the
thought like converter.
No,
DC
it is
to
not
AC.
like your converter, but think in the way of power transformation.
Okay, sir. That I understand, sir. Like regenerative braking.
In that way we are having. Okay.
Thank you, sir.
Oh, okay. Yes, next.
Good evening, sir.
Good evening.
Sir, in single phase full control bridge converter with RL load.
Single phase
Full control bridge converter with RL load, sir. RL load.
RL, yes. Without freezing diode.
Yes, sir. Without freewheeling.
Just a minute.
Output in this slide, so only, sir.
Yes.
Output V output average, sir.
V output.
Average. V not average.
Yes. Expression you want.
Yes, sir.
Yes.
In that first beginning of 1 by pi, how to get, sir? I can't understand. 1 by pi.
Okay. Yes. I will explain. You can check whatever the waveform we are having from 0 to pi, na?
Yes, sir.
Same is repeating from pi to 2 pi.
Okay.
So that's why it is a 1 by pi.
In
Periodic angle is pi.
okay, sir. In some expressions, we are taking 1 by 2 pi, no, sir.
No, that is in half wave control rectifier, na?
That is half wave.
In full wave, we need to take that 1 by pi only, because we are having the periodic angle is generally we take pi divided by pi or divided by 2 pi. It depends on the periodic angle of that periodic function, na?
Okay, sir.
In the half wave, we are having, if you recall, in the half wave, it is like, let us consider the purely resistive load. Okay. We are having
Yes.
the waveform from 0 to alpha, it is 0.
Yes, sir.
Alpha to pi, it is same as that of the supply voltage.
Yes, sir.
Pi to 2 pi, it is 0, na?
Yes, sir.
So whatever the waveform we are having from 0 to 2 pi, that was repeating, na, from 2 pi to 4 pi. So that's why we took there periodic angle is a 2 pi, but in this case it is a pi, na?
Okay, sir. Understood.
Yes, that's why it is a pi, right?
Sir, another doubt, sir.
Yes, please.
Sir, in electronics, the single phase half and full wave rectifiers, the efficiency is particular in 22 or 47. In power electronics, the circuits or efficiencies determined in any.
No, circuit efficiency or converter efficiency means simply your output power divided by input power.
Is it any particular number, sir?
No, generally in power electronics, the efficiency is comparatively high because we are having the lossless switches, no?
Yes, sir.
Right?
Yes, sir.
The only thing is it depends on your firing angle actually. If we are having the control rectifiers, then it depends on the firing angle.
Okay.
Suppose we are having the resistive load, na? If I keep the alpha value is very high, then it is like from 0 to that high value of alpha, our output power is like a 0 only, right?
Sir,
So according to alpha, your efficiency will change here, right?
okay, sir. In ripple factor, sir.
Ripple
Then-
factor is that we'll discuss while discussing one of the numerical. Actually, the thing is the two things only you need to memorize. One is the form factor and second one is the ripple factor. Form
Okay.
factor is nothing but RMS divided by average value.
Okay, sir.
RMS we already know how to find V0 RMS, V0 average.
Yes, sir.
So
Yes,
if you
sir.
take the ratio of these two values, you will be getting the form factor. And the ripple factor is like under root form factor square minus 1.
Okay, sir. Understood.
Right?
Sir, one sir. Hello, sir.
Yes, please.
Sir, 11F, sir, 11F.
11F. Okay, huh?
Sir, can you once explain that I1, IT2 and IS, sir? Cannot understand properly.
IT1, IT2 and IS, na? Okay.
Yes, sir, yes, sir.
Yes. This is purely resistive load,
Yes, sir.
bridge configuration. Yes or no? From alpha to pi, which two thyristors will be in on state?
From alpha to T1 and T2, sir.
T1, T2 are in on state, na? Alpha to pi.
Yeah, yes,
So
sir.
if you check the circuit diagram, yes. Yes. From alpha to pi, T1, T2 are in a conduction mode, na?
Yes, sir.
So current is flowing from Vs, T1, load, T2, and again back to the Vs,
Yes, sir.
right? So can I say that this I0 is equal to IT1 is equal to IS, which is equal to IT2 also?
Sir, one.
Yes or no?
Yes.
Yes. We are having only one loop, na?
Yes, sir, yes, sir.
And in this loop, we are having four currents: IS, IT1, I0, and IT2.
Yes, sir.
So can we say that all these are equal,
Okay, sir, okay, sir.
right? So IT1 is equal to IT2 is equal to IS is equal to I0. I0 we know, right? So that's why here during alpha to pi, I have shown there as, just a minute, 11F, na? Yes. Alpha to pi, I0 is same as that of IT1, IT2 is same as that of your I0.
I0.
Right? And next one more thing, alpha to pi, if you check alpha to pi, just now we discussed during alpha to pi. Yes, alpha to pi, here it is. Yes, IS is also equal to I0, na?
Yes, sir.
So IS waveform will be like this, same as that of I0,
Okay, sir.
right? Next, pi to pi plus alpha, what will happen? All the four switches off state, na?
Okay, sir.
So IT1, IT2 0, IS is also 0, I0 is also 0, right?
Yes, sir.
Pi plus alpha to 2 pi, what will happen? Let us discuss. From pi plus alpha to 2 pi, you can check. Yes, during this interval. Here you can check IT1 and IT2 are open, na? Means thyristor T1, T2 are open.
Yes, sir.
So can we say that IT1, IT2 are 0?
Reverse. Yes, sir.
So that's why from pi plus alpha to 2 pi, I have shown here. Yes, IT1, IT2 0. Is this clear? Now let us discuss from pi plus alpha to pi why the IS is negative, right?
Yes, sir. Tell me, sir.
Pi plus alpha 2 pi, you can check. Current is flowing like this, na? Vs, T3, load, T4, and again back to the Vs. In this loop, current is flowing.
Yes,
So
sir.
you can check in this loop, I0 is downward direction only, means I0 is positive,
Positive. Okay, sir.
right? I0 is positive only in a downward direction. But
Yes,
the
sir.
same I0 is flowing like this from here through T4, it will reach to this branch. But in this branch, how the current is flowing, you can check the current direction like this. So in this branch, the current is in the downward direction, na?
Yes, sir.
IS positive means we considered it is upward direction. So if the IS is negative means if IS is in a downward direction means IS should be negative, na?
Yes, sir.
So that's why from pi plus alpha 2 pi, your I0 is positive, but IS is negative,
Opposite.
right? It is opposite. Is this clear?
Okay, sir.
Right.
Hello,
Okay.
sir.
Yes, please.
Sir, I not got the inverter operation in last circuit.
Oh, okay, inverter mode operation.
Yes, sir. Yes, sir.
Okay, okay. Yes.
Sir, how the circuit will operate, sir? I have not got
How?
how the circuit will operate, sir. Actually, sir, will you please explain in short, sir?
Okay, okay. Yes, please listen. Actually, we are keeping alpha greater than 90 degree.
Yes, sir.
So suppose that omega t is equal to alpha means at this instant I am turning on thyristor T1, T2.
Yes, sir.
So when T1, T2 turns on means T1, T2 conducts. At this instant you can check alpha. Sorry. Yes, here it is. Alpha. It is still less than pi na?
Yes,
So that's why our supply voltage is positive only.
yes,
Current will flow from Vs T1 load T2 and again back to the Vs. In this loop current is flowing.
yes, sir. Got it.
Right? So inductor is storing the energy.
Yes, sir.
But our inductor will store energy only till alpha to pi.
Yes,
After pi, you can check supply voltage is negative. Supply voltage negative means it is like a minus here and plus here.
yes, sir.
So supply voltage will try to circulate current in opposite direction, but inductor will release the energy.
Okay, sir.
So when inductor releases the energy, and here you can check EMF we have placed, it is a reverse na.
Yours, sir.
So that EMF energy and inductor energy both will be adding now.
Yes,
So therefore these two will be opposing the supply voltage. So resultant current will be through T2, T1 only,
okay,
right? So when current flows through T2, T1 in opposition to that of the supply voltage, you can apply KVL to this loop. You can apply, yes, it is a minus V0. Minus V, yes, is equal to 0 na?
Yes, sir.
So minus V0 minus Vs is 0 means V0 is equal to minus Vs. So
Yes, sir.
V0 is negative. So that's why here we are having V0 is negative.
Sir, but in the negative half cycle we have discussed after pi, sir, T3 should be in the conduction. No, sir.
T3 should be in
T4.
forward bias mode.
Forward bias. Yes.
No, but thing is we have not applied the gate signal to T3 na. We are applying the gate signal to T3 at pi plus alpha.
Sir.
Yes
Sir,
or no?
means after pi also T3 and T4 will not in conduction.
Yes, yes. T3, T4 will conduct at pi plus alpha.
Pi plus alpha. Okay.
We are applying the gate signal to T3, T4 at this instant na. Because
Okay.
what we have done, alpha we have maintained the greater than 90 degree.
Yes, sir.
If alpha is greater than 90 degree means I am turning on T3, T4 at this instant,
Yes.
right?
Yes.
And from pi plus alpha again what will happen? T3, T4 conducts. So current will be flowing from, yes, Vs, T3, inductor, T4 and again back to the Vs. Again your inductor go on storing the energy, right?
Yes.
So V0 you can apply the KVL to this loop. Minus V0 plus Vs is equal to 0. Okay. So V0 is equal to Vs. So you can check here V0 is positive.
Okay.
After 2 pi supply voltage polarity is reversed na. After 2 pi supply voltage polarity is reversed, means here it is opposite, plus here minus here. So again inductor go on releasing the energy, T3, T4 will be in a conduction mode, right? So
Okay.
here the thing is inductor is releasing the energy for a long time. And this is possible only due to the EMF E, because EMF we have placed the opposite na.
Yes.
And EMF and inductor energy both are adding here. That's why it is possible.
Sir, there is any requirement for the inductor value, sir? It could be high or low means in this circuit.
Generally the thing is here we are using whatever the inductor is there in the machines,
Yes.
and
sir.
whatever the EMF induced in the machine na, that we are connecting it as an reverse.
Okay. Okay.
It's only terminals we are interchanging.
Yes. Sir.
So definitely your inductor value required is high only,
Yes. Sir.
right?
Yes. Sir.
Okay, okay.
Sir, one more doubt is there.
Yes, please.
Sir, in RLE load waveform.
RLE load waveform. Okay.
Yes.
Yes, huh.
Sir, in this waveform, I not got the effect of inductor, sir, means inductor releases energy and the E assist it or opposes it. Sir, I
Yes.
don't got that point.
Actually, the thing is, here value of inductor is high.
Yes.
Due to that, in the output voltage, you will not observe the effect of EMF E.
Yes. Sir.
Means from alpha to theta, our inductor is storing the energy through T1, T2.
Yes. Sir.
From theta till pi plus alpha, inductor releases the energy,
Okay, sir.
right? So EMF E effect is not observed, but you can, if you check that low value of inductor, na, in that case, you will get the E portion in the output voltage. It is like this,
Yes.
right? It depends on the value of PL actually, right?
Yes. Sir.
Okay.
That means in a low value, we have get this E portion. In the waveform.
Yes, yes, yes. We'll be getting this type of waveform, and E portion will be there, right?
Yes. Yes.
Okay. Okay.
And sir, one more last doubt, sir.
Yes.
Sir, in a R load, we have not considered the circuit turn off time, sir.
In which load?
R load, sir, R load. Which R load? RE load or R load?
Purely resistive.
Yes, sir.
We can find it. Doesn't matter. Okay. Let me check.
Yes, sir. This R load.
Here, na?
Yes.
Yes, I have written pi minus alpha by omega. While discussion, actually, I wrote here by mistakenly it as a VM. That is a PIV actually wrote. PIV is VM, na?
Yes, sir. PIV is
TC should be like no. This is TC, na? Let me correct. Conduction time is pi minus alpha by omega. It is fine. TC should be
circuit turn
over.
off time.
No. It is a 2 pi minus pi. We need to consider the reverse voltage, na?
Yes, sir. We have to.
Pi till 2 pi is reverse. 2 pi minus pi. I'm sorry. It is a pi by omega. Right?
Okay, sir. Okay.
Okay. Actually, I wrote there conduction time. Okay.
Sir, this is circuit turn off time, sir.
Yeah, this is circuit turn off time. TC means circuit turn off time.
Okay, okay, sir.
Right. Yes, next.
Hello, sir.
Yes, please.
Sir, how in case of RL load of a controlled rectifier, I naught is P is getting magnitude at magnitude of I naught is peak at before pi, sir. How can we say, sir, that one?
Please repeat.
Sir, in case of RL load, how can we say that the magnitude of I naught is maximum before the pi?
Magnitude of I naught.
Yes, sir. Or
Before
IL,
the
sir.
pi.
IL, sir. IL.
Magnitude of IL, inductor current.
Yes, sir.
Is
Getting maximum, sir. You said no, sir. Before
Just
pi,
a
it
minute,
will be
just a minute.
maximum.
in which circuit you are saying?
Sir, in case of half control, half wave, sir.
Half your RL load.
Yes, sir.
Okay. Half your rectifier you are saying, na?
Yes, sir.
Just a minute. I will let you know. Yes. Suppose half wave controlled RL load means this circuit only, right?
Yes, sir. Yes, sir.
Okay. So your doubt is how we can say that value of IL, right?
Yes, sir.
Before pi, just before pi, it is a maximum, na?
Yes, sir.
Okay, just a minute. I will explain. Yes. So here we are having the supply voltage Vs, right? Omega t 0, right? Vs is like this, na?
Yes, sir.
We are having IL is like this. IL or I0 you can say, right?
Yes, sir.
Because inductor is connected in a load, na? So it is I0.
Yes, sir. Series. Yes, sir.
Suppose at alpha I am applying the gate signal, right? And we are having the waveform like this. After alpha it is increasing, okay? Just before pi, it starts decreasing, na?
Yes, sir.
This is like beta, and this type of waveform we're having, right?
Yes, sir.
So this angle, this corresponding angle, we consider it as a theta. Na? Now you
Yes,
can
sir.
check if I0 is like this, how will the REL, sorry, voltage across resistor. Suppose this is VR, this is a
Oh.
VL, na? Yes.
Yes, sir.
If I0 is like this, how will the waveform for voltage across resistor? We know VR is equal to what? I0
In
into R.
phase,
Na?
sir.
So
Yes, sir.
the VR nature will be same as that of your I0 nature. The only change in the magnitude, na?
Yes,
So you can check after from alpha I0 is non-zero. So therefore your VR also non-zero, right?
yes,
So
sir.
it is like this. At this instant it reaches peak value, and after that it will be like this. So this beta and this beta will be same here, and this is like your theta. Okay, this is like your theta we consider. Now
Yes,
check it
sir.
carefully here. Yes, this is your VR. Huh?
Yes, sir.
Now if we suppose thyristor is in a conduction mode,
Yes, sir.
Vs is positive plus minus. So if I apply KVL to this loop, it is like a plus Vs minus VR minus VL na, is equal to 0.
Yes, sir.
So from this, can we write VL is equal to Vs minus VR.
Yes, sir.
So VL means what? Voltage across inductor. It is a difference between supply voltage and resistor voltage.
Yes, sir.
So now you can check here. At alpha, resistor voltage is 0 because I0 is 0 na.
Yes, sir.
So what is the difference between Vs and VR? It is this much value na. Let me use the different color. Yes. So you can check this much value is nothing but your VL at alpha. I am saying.
Yes, sir.
After that, VR value is decreasing and Vs waveform is like this. So if I take Vs minus VR difference, it will be like this. Vs minus VR is this value minus this value na.
Yes, sir.
At theta, what is happening at theta? Both are becoming 0 na.
Yes, sir.
So you can check here. Yes, at theta, at omega t is equal to theta, VL is equal to 0. So means what? Vs is equal to VR, right?
Yes, sir.
Before this, yes, before this instant, before theta, it was like Vs is greater than VR, na?
Yes, sir.
So before theta, Vs is greater than VR. So let me write before theta, Vs is greater than VR, na? So it is like a VL is a positive. Yes or
Yes,
no? Because VL
Yes,
means
sir.
what? It is a Vs minus VR, na?
Yes, man.
So Vs
Yes, sir.
minus VR, VR is less than, Vs is greater than VR. So VL is positive. So what is VL? VL is nothing but L into DIL by dt. This
Yes,
is
sir.
positive. So can we say that DIL by dt should be positive?
Yes, sir.
Whether
It's
we are having a
total.
negative value of inductor, we
No,
don't
sir.
have a negative value of inductor, na? We are having only
Yes,
positive
sir.
value of inductor. So DIL by dt is positive. DIL by dt means what? Rate of change of inductor current with respect to time. So that's why here our
Yes,
current
sir.
is increasing. At theta, voltage across inductor becomes 0. After theta, you can check.
Yes.
After theta, you can check. VR is greater, Vs is less, na?
Yes, sir.
So VR is greater, Vs is less means VL will be negative, na?
Yes, sir.
So VL negative means your DIL by dt negative.
Yes, sir.
This current should decrease. So that's why this is a peak value.
Sir,
Before
but we
this-
are drawing,
Yes, yes.
so but we're drawing the VR based on the I0 only, no, sir. Before
Yeah, we
the
are drawing the VR based on the I0. Definitely. First of all, the I0 will circulate.
Yes, sir.
But your VR will be generated na here. Generated I cannot say, but with the help of Ohm's law, definitely some voltage will appear across the resistor.
Yes, sir.
And that voltage changes according to I0.
Yes, sir.
Right? So that's why we're getting this type of shape.
Okay,
It
sir.
is not like that ki first of all we're getting VR. No, definitely first of all I0 is circulating. After
Okay,
that
sir.
the VR will be we are getting. And that VR magnitude, whether this point will be here, whether this point will be near to pi, very close to pi, or whether this point will be here, it depends on value of your resistor as well as your I0 value,
Okay, sir.
right? So if
Sir,
resistor value is high, your VR will be like this, na? Let me draw here.
Yes, sir.
Your VR will be like this somewhat. So
Sir, if
your
resistor
theta will be shifting to the left side, right?
okay, sir, if resistor is having higher value, it means it will come for more than less than very under it will not close to 5, sir. It will be far more than 5, no, sir.
Yes, please repeat. If R value is more.
If R value is more, it will not close to pi. Before only it will come, no, sir.
Yes, yes, it will be far away from that pi, right?
Yes, sir. Sir, another one,
It
sir.
is like
Sir,
a more resistive circuit. Na? If in the RL circuit, if R value is more, then it will be like will be moving towards the pure resistive type thing. Na?
yes, sir. Yes, sir.
Yes, yes.
Sir,
Okay, next.
another one, sir. Sir, how to determine the theta point, sir? Means you said, no, sir. Now, how to find it, sir? Theta.
Generally, the theta value, finding of the theta value. Okay, for the undergraduate study level, we are not discussing it. But definitely, if you go for the PG, MTech, ME, in that case, there is a they have added into the syllabus. But if you want to find the simply what you need to do after alpha, okay, from alpha till theta, we need to apply the get pulse to this pulse. We need to apply KVL to this loop. Okay, once I get the KVL to this loop, then we'll be getting like expression between Vm sin omega t minus I0 into R minus L into di0 by dt, right?
Yes, sir.
Next, what we need to do from that, we need to find the value of I0, expression for I0.
Yes, sir. We derived one equation.
Yes, yes.
Yes, sir. We have derived
We
equation,
have
no, sir,
written
for
that
I0.
expression. Yes, we have written that expression. Please listen. So from that I0, we're having I0 is some expression, right? So from that
Yes, sir.
I0, what I need to do at omega t is equal to theta. Okay. We need
Yes,
to
sir.
write it as a Vs is equal to Vr. Na?
Yes, sir.
What is Vr? We need to write Vr is equal to I0 into R. So in
Yes,
this
sir.
expression, I need to replace omega t with theta, and I need to replace Vr with Vs. So from that, you can get theta value,
Okay, sir.
right? Okay.
Yes, sir.
Hello, sir.
Sir, sir, I have
Yes,
asked
please.
that one about at previous classes, sir, regarding thermal say operating
Yes,
regions.
yes. I will tell you it. Give me some time. Okay.
Okay, sir.
Sir,
It is there in my mind. I will tell you. Okay. I have not forgotten it. Okay. Don't.
Yes, sir. Okay, sir. Thank you, sir.
Okay. Okay. Yes. Yes. Yes.
Sir,
Next.
slide
yes,
number
please.
25.
Slide number
25, sir.
25. Okay. Yes.
Sir, in that during pi to pi plus alpha, is that, sir, df, I naught equal to df?
Yeah. I naught is equal to IDF.
Oh, yes, sir, because T1 and T2 is off and IS is also
Correct,
0.
correct. I naught is equal to IDF. Or even if you want to draw the waveform of IDF, na?
Yes, sir.
Yes. How it will be waveform of IDF? Suppose if I want to draw I naught, we are having a constant current, na? Suppose if I want to draw the IDF waveform, how it will be? 0 to alpha, we are having a freewheeling diode will be in conduction mode, na?
Yes,
So
sir.
0 to alpha, IDF is equal to I0.
Yes,
Alpha
sir.
to pi, IDF is 0.
Yes.
Pi to pi plus alpha, IDF is equal to I0.
0.
Pi plus alpha
Yes,
to
sir.
2 pi, IDF is 0. And 2 pi to 2 pi plus alpha, it is again I0, right?
I0. Yes, sir.
Right.
Okay,
So
sir.
our load current I0 means the combination of your thyristor current and your freewheeling diode current, right?
Okay. Yes, sir.
Yes, yes.
Thank
I
you,
think
sir.
in one of the booklet question they have asked, we'll discuss that while solving that question, okay?
Okay, sir.
Yes, next.
Hello, sir.
Yes, please.
Sir, in the RLE load, the inverter mode of operation. Sir, can you take that?
In
Inverter mode of operation.
inverter mode of operation, RLE load. Okay. Just a minute. Yes, here it is.
Sir, so in this, actually, the inductor's value is high, sir.
Yes.
So whenever it is like, it is only able to charge from alpha to pi. And then
Yes.
it is, so it will be able to store only less amount of energy, sir. So when it is,
Comparatively, yes.
Sir. So, will it be having so much of time to release that amount of stored
Release
energy
that-
till the next?
Okay, okay. Actually, the thing is, you can check here. Here, your EMF is assisting to inductor, na?
Sir.
Previously, whatever we discussed in those circuits, it was like a inductor was opposing, EMF was opposing.
Sir.
But now here, E is also assisting to the inductor. So that's why resultant their energy will be greater than that of the supply energy.
Okay, sir.
Then and only then it is possible to get this waveform, na? Just a minute. Yes, this waveform.
Sir.
If
So
your L value is less, yes, we cannot, yes, continue this conduction till pi plus alpha, right? So we need to select the value of L here such that the conduction should be continuous and the combination of L energy and the E energy should be greater than your Vs, right?
Yes, sir. Sir, so when we are drawing that waveform, it's not the amount of energy which is stored in this inductor alone. It is plus that energy of the EMF also.
Yes,
sir.
yes, plus that of EMF, right? But here you can check while drawing the waveform of V0, we need not to worry about the energy, na?
Sir.
For I0 it is affecting, right?
Sir.
Right. Okay.
Sir, and one more doubt in last class,
Yes.
previous class,
Yes.
center tap transformer with R load, you are told the input power factor, sir.
Center tapped
Sir,
transformer
so in
with
that
L load.
R load, sir.
Okay,
Sir, in
R
that,
load.
input power factor you are told, sir.
Yes.
Sir, so in that I could not get why we had not taken VSRMS into
No, actually
IS,
the thing is, you can check the secondary winding of the transformer.
Sir.
It is divided into two parts.
Yes,
Whether
sir.
the current is flowing in full secondary winding, okay, whether the current is flowing in this full secondary winding for all the time, no, na?
No.
It is like from omega t is equal to alpha to pi, it is flowing through the upper part.
Sir.
At that time, your lower part current will be 0.
Sir.
And during the second interval, that is from pi plus alpha to 2 pi, okay, it is like a second lower part current is a non-zero and upper part current is 0. So that's why here we cannot blindly take it as a 2 Vs into that your secondary winding current, right?
Sir.
So
Sir,
we need to first find the individually the separate VA rating for the upper part, separate VA rating for the lower part, okay?
Sir.
And we need to multiply it with 2 actually. Means any one part we need to find, and after that we need to multiply it with 2, right?
Sir. So we
We are
are
having one numerical. We are having one numerical. Actually, that was related to your diode center tap transformer configuration.
sir.
But there we need to use the different concept. We will discuss it at that time. Okay.
Okay, sir.
Right.
Okay, thank you, sir.
Okay. Okay. Yes. Yes. Next.
Hello, sir.
Yes, please.
5F, sir.
5F. Okay.
Yes, sir.
Yes.
Sir, here voltage across thyristor 1 and 2 equal to source voltage by 2. How it will become, sir?
Okay. Okay. You can check. Either you can apply KVL to this loop. That
Yes,
is
sir.
Vs T1 T3.
Okay, sir.
Or you can apply KVL to this loop. Vs T1 V0 T2. Okay.
Yes, sir.
Both the ways you can take here. Yes, let me show here. Suppose if I apply KVL to this loop, Vs T1 load T2 and again back to the Vs. It is like a minus Vs.
Yes, sir.
Minus VT1 minus V0 minus VT2 is equal to 0. But what is our V0? V0 is 0, na?
V0 is 0.
So can I write VT1 plus VT2 is equal to what? Minus Vs.
Minus Vs. Okay, sir.
What is the VT1? Voltage across thyristor T1. What is VT2? Voltage across thyristor T2. Yes or no?
Yes,
So
sir.
thyristor T1 and T2 both are in which mode? Forward blocking mode.
Forward blocking mode.
Both are both the thyristors are made up of the same material, same 4 layers they are having.
Yes,
Three
sir.
junctions they are having. Okay, so can I
Ah.
say that the voltage blocked by the each device will be same equal,
Yes, sir.
right? Yes or no? So that's
Yes,
why
sir.
this voltage will be getting divided equally. VT1 is equal to VT2 is equal to minus Vs by 2.
Okay, sir.
It is like suppose in a circuit you are having the two resistors and those two resistors are having the same value now, and suppose
Yes.
across that the voltage is Vs, it is equally divided, same thing, right?
Okay, sir. 11F, sir.
11F. Okay. Yes.
Here, IS RMS equals to I naught RMS. How, sir? I naught and IS.
IS RMS is equal to I naught RMS. Okay.
I naught
Okay.
RMS.
Generally, yes. Think about the RMS value. What is the RMS? RMS means the square root of mean of squared value, na?
Yes, sir.
So square root means we need to put it in square root. Mean of the squared value, that is the average of the squared
Average.
value.
Okay,
Average
sir.
of squared value, na?
Yes,
So if
sir.
I take the square of this, so what is the square of this? I0 square. So it is alpha 2 pi, it is a positive value. Pi plus alpha 2 pi, it is a positive value.
Yes, sir.
Yes or no?
Yes, sir.
You can check I0 square waveform and you can check IS square waveform.
Sir. Yes,
Alpha
sir.
2 pi, IS is positive, so its square is positive. Pi plus alpha 2 pi, IS is negative, its square will be positive only, na?
Okay, sir. Okay.
So now think about IS square and I0 square waveform, whether these two will be same or different.
Same, sir.
Same. So if I0 square waveform and IS square waveform both are same, so what about the I0, average of that I0 square and average of the IS square, same or different?
Same, sir.
So if you put it into square root, you will be getting the same value, na?
Yes, sir.
So that's why I0 RMS and IS RMS are same, right?
Yes, sir. Sir, another one, sir. Hello, sir.
Yes,
Once explain, sir, majority charge carrier and minority charge carriers are high breakdown voltage can be achieved by inserting lightly doped material on one side of PN junction.
Okay. Actually, the thing is, if you add the lightly doped material, okay, into the device structure, lightly doped material means what? It is having a very less number of charge carriers. Okay,
Yes.
and we are increasing its width. We are increasing the width of that lightly doped layer. Okay, the thing
Yes,
is,
sir.
when the lightly doped material we are getting, it is getting added into the device structure, and if we apply the voltage, then suppose that lightly doped layer, if it is a part of a reverse bias junction, na,
Yes,
then
sir.
it is like that layer, okay, will be it is like due to that layer, our depletion layer which is in a reverse bias mode, and that depletion layer in a reverse bias mode it is increasing, na?
Yes,
So
sir.
it is like that depletion layer will be having a more scope to increase, because the width of the depletion layer is high, na? Width of that layer is high. Let me show here.
Width will be increased, no, sir?
Yeah, just a minute. I will show you. So suppose I am having, let us consider about your simple PN junction diode. Okay, that is a power diode. It is like P plus, it is like a N plus, and here it is a N minus, na? Anode, and here it is a cathode. We are having only one junction, na? This is a junction.
Yes, sir.
Now you can check here. If I maintain the reverse voltage, means here it is minus, here it is plus. So this junction will be in a reverse bias mode.
Yes, sir.
So width of the depletion layer across this junction will be means minus here. Yes or no?
Yes, sir.
And here it is a plus. Right? If we go on further applying the voltage, na? If we go on further applying the voltage, yes, it is like we are having this much of space, na, to increase.
Yes, sir.
But whereas if you check in your signal diode, in signal diode actually we are having the very less width. I cannot draw this much. So it is a P and N we are having. This is a anode and this is a cathode now.
Okay,
So in
sir.
signal diode, what is happening? This is a minus and suppose this is plus. Definitely we'll be having the depletion layer here. Right?
Okay, sir.
But how much space is available for the this depletion layer to grow? Very less space, na?
Yes, sir.
Here where the depletion layer is having a very high scope, high space available to grow. But in this case, the depletion layer is having a very less space to grow. So due to that, it is having a less voltage blocking capacity. And it is having a high voltage blocking capacity. Means whether the device will block how much voltage, it depends on till the breakdown of that layer, na?
Okay, sir.
And when the breakdown of the depletion layer will take place, once that breakdown once that depletion layer will reach till its maximum limit, that maximum limit will be decided by this space also. Are you getting the point?
Okay, sir.
Due to that, yes, we are getting a high voltage blocking capacity here, right?
Yes, sir.
Is this clear? Okay. So,
Yes, sir. Yes, sir.
okay. Okay.
Sir,
Yes, please.
what is the freewheeling diode action, sir?
Freewheeling diode action. Okay. Freewheeling diode is nothing but that diode we particularly placed there in the case of REL load. So that our inductor, load inductor can release the energy through that path. That is a low resistance path it is providing. And what is the advantage of that? When inductor releases the energy through the freewheeling diode, na, your V0 will not be having that negative pulse. If negative pulse is not there from pi to pi plus alpha or from 2 pi to 2 pi plus alpha, your V0 average will be getting improved, na?
What, sir?
If the negative pulse is not there in the V0 waveform,
Yes, sir.
whether your V0 average will increase or it will remain same, it will increase. You can check V0 waveform REL load with freewheeling diode and V0 waveform for REL load without freewheeling diode. Freewheeling action means your freewheeling diode, your diode, it is a normal diode only. That is allowing the inductor to release the energy. Is this clear?
Okay, sir. Sir.
Yes. Next.
Hello, sir.
Yes, please.
Sir, in this part only, RL load where we are having a freewheeling diode. Sir, I
Okay.
wanted to ask when the current is flowing
When the current
pi
is
to pi
flowing,
plus alpha, then the current will be through the freewheeling diode. Then it will be decreasing or it will be constant.
it depends on what is the value of your inductor. If value of inductor is high, right,
Yes, sir.
you will be having the constant current. If the value of inductor is low, then it will be decreasing.
Okay, sir.
Are you getting the point? Right? It will be decided by the value
Is
of
in
inductor.
RLE load, sir. In RLE load, sir.
Will you please repeat?
Sir,
In RLE load, yes.
Yes, sir. Sir, thereby we haven't used that concept that when Vs is greater than E, then only thyristors will be turning on and
Okay,
otherwise
okay.
not.
In RLE load and for high value of inductor, you are saying, na?
Yes, sir. In the part of 0 to alpha only.
No, no,
when
no.
there will be no energy in inductor.
Means at the very first cycle, you are saying.
Yes, sir.
No, actually, that very first cycle I explained only at the very start of that REL load only, right? But the thing was, or the purpose of that explaining that is in order to understand how at the very first cycle, how the voltage and the current nature will be. But you can check that is limited. First thing is that time period is very small, na, 0 to alpha we are having.
Yes, sir.
And that is occurring for very first cycle only. You can check for the next cycle of the supply, whether we'll be having that same waveform there.
Yes, sir.
whether it will be there, same waveform will be there or not. Same waveform will not be there na, because that during 0 to alpha means what, or very first cycle means what, the behavior or the nature of the V0 and I0 will be there only for the very first cycle only. If supply completes one cycle na, after that you cannot observe that very first cycle waveform there. So generally we are neglecting it na, because the thing is it is present for very short time interval. Okay, and we are having the supply, it is like in 1 second it is completing 50 cycles. So you can you can check in 1 second we are having a supply that is completing 50 cycles. Okay, and in that also if you check very first cycle, in the very first cycle also we are having only 0 to alpha, that term present. So that is very less time na.
Yes sir.
So
Sir,
that's why for periodic signal, okay, we are neglecting it.
सर अगर जैसे इसकी वेवफॉर्म सीआरओ पे देखते होंगे तो वेवफॉर्म क्या फिर सीधा अल्फा से ही दिखाई देती है क्या?
वेवफॉर्म सीधा आपको जो है ना कंटिन्यूस साइकिल जो है ना वही वेवफॉर्म दिखेगा. सीआरओ पे वेरी फर्स्ट साइकिल वेवफॉर्म दिखेगा क्या? एज सुन एज यू टर्न ऑन द सीआरओ ना, सपोज आई एम हैविंग वन सर्किट, ओके, एंड आई हैव कनेक्टेड सप्लाई टू दैट सर्किट, और फिर मैंने उसको सीआरओ कनेक्ट किया और मैंने क्या किया कि सप्लाई टर्न ऑन किया है. सप्लाई टर्न ऑन करते करते अपना 1 सेकंड चला जाता है. सो ड्यूरिंग दैट 1 सेकंड मेरे पास सप्लाई की क्या है 50 साइकिल्स है ना. सो उसमें आपको वेरी फर्स्ट साइकिल का जो 0 टू अल्फा का टाइम पीरियड है और उसका जो वेवफॉर्म है वो सीआरओ पे ऊपर दिखेगा ही नहीं. सीआरओ आपका क्या करता है, लाइव वेवफॉर्म दिखाता है.
ओके सर.
आर यू गेटिंग द पॉइंट? जस्ट अ मिनट, लेट मी शो यू. You can check here, frequency 50 hertz means what, in 1 second कितने cycles है? 50 cycles ना?
Yes sir.
So corresponding to 1 cycle, for 1 cycle कितना time है? For 1 cycle it is like a 1/50 ना?
1/50.
It is a 20 into 10 to the power minus 3, 20 मिलीसेकंड का टाइम है ना ये?
Yes sir.
ये क्या है, एक साइकिल कंप्लीट करने के लिए बोल रहा हूं मैं. और अगर आप देखोगे वेरी फर्स्ट साइकिल में भी ये ओमेगा टी 0 नहीं, ये V0 0 टू अल्फा टू पाई, राइट, एंड आफ्टर दैट वी आर हैविंग द वेवफॉर्म लाइक. सो ओनली 0 टू अल्फा पीरियड के लिए ये अपना V0 0 था ना.
Yes sir.
So you can imagine one complete cycle of the supply means 0 to 2 pi. ये पाई हो गया, ये पाई प्लस अल्फा हो गया, ये 2 पाई हो गया ना. सो इसके लिए कितना टाइम लगता है, 20 मिलीसेकंड.
Yes sir.
तो
सर
इसके लिए
ये
कितना टाइम लगेगा? इट इज वेरी लेस टाइम ना.
सर ये 0 टू मतलब ये 0 ही होगा या ये ई होगा?
कौन सा?
सर
ये
ये
इट डिपेंड्स ऑन, अगर आप आरएल सर्किट कंसीडर करोगे तो 0 होगा, अगर आप आरएल ई बोलोगे तो ई होगा, राइट. आरएल ई बोलोगे तो ई होगा, राइट. सो इट विल बी लाइक ई. सपोज आपको अगर ई कंसीडर करना है आरएल ई, तो ई कंसीडर कीजिए. तो यहाँ पे ई होगा, एंड आफ्टर दैट क्या होगा, फिर आफ्टर दैट कंटिन्यूअस, अगर मेरा कंडक्शन है, कंटिन्यूअस कंडक्शन है तो इस टाइप से होगा ना ये.
यस सर.
यस और नो?
यस सर.
तो अगर इस टाइप से वेवफॉर्म आ रहा है मेरा एक साइकिल के लिए, फिर सेकंड साइकिल के लिए सप्लाई के, फिर थर्ड साइकिल के लिए सप्लाई के, इस टाइप से अगर वेवफॉर्म आ रहा है ना, सो यू कैन चेक ई कब अपेयर हो रहा है, ओनली फॉर वेरी फर्स्ट साइकिल ना.
Yes,
तो ये आपको सीआरओ के ऊपर दिखेगा ही नहीं, क्योंकि इतना टाइम मेरा 20 मिलीसेकंड है, तो ये टाइम क्या हो गया, बहुत लेस टाइम हो गया.
Yes, sir.
अभी हम बात कर रहे हैं 1 सेकंड चला भी गया, उतने में सप्लाई के 50 साइकिल्स हो गए.
Yes, sir.
कैन यू इमेजिन? और सीआरओ अगर अपना सीआरओ लाइव वेवफॉर्म दिखाता है, सीआरओ स्टार्टिंग वाला वेवफॉर्म दिखाएगा ही नहीं, राइट.
Okay, sir. मतलब कंटिन्यूअसली दिखेगा.
यस यस, कंटिन्यूअसली दिखेगा, राइट.
Okay, sir.
Okay.
Thank you, sir.
Yes. Okay.
Hello, sir.
Yes, please.
Sir, 32F.
32. Okay.
Yes.
Yes.
Sir, why are you considering mod VS here?
Okay. Because yes, you can check this circuit. generally before this whatever we discussed now for half controlled bridge half controlled and RE load,
Yes.
means it is like only one thyristor was there, supply was there, and RE load was there, right?
Yes, sir. Yes.
So in that case, we're having the concept like if Vs is negative, then thyristor will be more negative. But in this case, it is like you can check if supply voltage is negative, means minus here plus here. Our these two thyristors na T3, T4, these two will be in a forward bias mode na.
Forward. Yes, sir.
Means there is a chance of getting forward bias of these two thyristors T3, T4. And
Yes,
here
sir.
we cannot directly compare this Vs and this E, because E is your positive and Vs is negative.
Okay.
So if I take this difference na, then it will be negative always. So in order to understand that, we need to consider, yes, the mod Vs concept here. Otherwise, it will be confusing only.
Okay. So VS
you
may
take
be
that
positive or maybe negative.
You can check. Huh? During 0 to pi, I am taking Vs minus E difference. It is fine because both are positive. Na?
Yes, sir.
So from this, can I say that during 0 to theta, Vs minus E is negative. So thyristor voltage will be negative. Thyristor will be in a reverse bias mode. After theta, Vs minus E is positive. Vs is positive means what? This side voltage is greater than that of this side voltage. So thyristor will be in a positive mode. That is the forward bias mode T1, T2.
Forward.
But in this case, how you can explain? When Vs is negative, so for that case, we need to consider the mod Vs only, because the thing is, even though the supply voltage is negative, but our thyristors T3, T4 will be in a forward bias mode. So in order to compare that, I have taken this, it as a mod Vs. Mod Vs means what? Yes, it is a negative, but we are considering the magnitude only. So if I draw the mod Vs, it will be like this, na, dotted one. Right?
Positive.
Yes. So
And
then
sir,
and only then we can take the difference of these two, na?
Yes, yes, sir.
Otherwise, what I need to do? I need to draw the E from 0 to pi. E is positive and pi to 2 pi E should be negative. And then I can compare the two negative values, E and Vs. That will be the one thing. But again, the students will get confusion or the question like, sir, why E is actually the constant? So why you have drawn that step, that square wave type of waveform? Okay. So this is actually explaining concept, right? Explaining technique, we can see. Yes, any other?
And sir, why freewheeling diode is not used in RLE load, motor load?
We can use, okay, or in some of the cases they are using also, okay. But it is the thing is again you are getting the same type of operation for freewheeling diode. Only when freewheeling diode is in a conduction mode, at that time your output voltage is 0, na?
Yes, sir.
Right. But the thing is, in the REL E load and motor operation is there. Already we are having a high value of inductor there.
Okay.
Right? And that will be sufficient, okay, to make your conduction is continuous, okay, and to get the voltage is sufficient, we can see. But in some of the cases they have given, generally we connect the freewheeling diode also, okay. But in this we don't have the configuration like RLE load and freewheeling diode, right?
Okay. And sir, why pure inductive load is not considered in full wave rectifier?
No. Pure inductive, if you check in real life or in practical case, we are having a standard loads like a resistive load, means your heater load type thing, right? RE load like a battery charger circuit type thing, okay. We are having some inductive loads, REL load, not a pure inductive, but REL load we are having, okay. And next we are having a motor load, DC motor load. These type of loads we are having. Pure inductive or the pure capacitive, we discussed that only to get the feel, because some of the times they have asked the question like pure inductive load, okay. So for that I covered that concept at that starting of your rectifier only, right?
Okay, means there might be some losses exist in that rectifier.
No, it is not like that. You cannot relate that with the losses, okay. But in real life, whether we are having a pure inductive loads, we don't have pure inductor, pure capacitive.
No.
Most of your load, you can check your induction motor, you can check your DC motor, it is RLE load. Battery charging circuit, where we are using the rectifier, we are using for battery charging circuit, it is RE load. we are using for heater element, it is a purely resistive load. Yes or no? We are using for DC motor, it is a RLE load. So generally in real life or in practical case, we don't have the pure inductive type of load. If we are having the pure inductive type of load, then it is supplied by the AC source. Are you getting the point? It is not supplied by the DC source, it is supplied by the AC source. And in capacitor also, if we are definitely we are having very rare capacitive type of loads, first thing. And if we are having the capacitive type of load, and then it will be supplied by the pure AC supply actually, right? So that's why in rectifier case, as the output is DC, so we are having this type of loads, right?
Okay. And sir, of the last 2-3 days, I have sent you one question that half cycle surge current rating of SCR.
I have given the answer, na?
No, sir. Below question.
You are the
told
another
that-
student. I don't know, but I have given the answer to that student also. Just a minute. It is simply what you need to do. Just a minute. Because we discussed that when a surge current flows through the device, then the device absorbs energy, that is I square T.
Yes.
So we need to equate that energy, and accordingly you can find the that current. Okay.
Yes.
I will forward it to you also. I think I will send to another student the same thing. Okay.
Okay, sir. And sir, one more general
Yes.
doubt that
Yes.
what is the difference between rectifier and converter?
No. Actually, the thing is, converter is your general thing. Converter means what? It is a circuitry which converts one form to the another form. That is a converter.
Yes, sir.
For rectifier, we can use the word converter. For DC to DC converter, also we can use the word converter. Okay.
Converter.
But if they give it as fully controlled bridge converter, then we need to understand it is a rectifier only. Is this clear?
Oh. Yes, sir.
Right?
Yes, sir. Clear.
Converter is a general concept, general thing actually. It is applicable for your AC to DC, DC to DC, etc. Right? We're
It
having
can
AC
convert to any
voltage,
kind of
controller,
quantity.
AC voltage converters also, right?
Okay.
Yes.
Thank you, sir.
Okay. Yes, next. Hello.
Hello.
Yes, please.
Sir, I have a doubt regarding this theta and theta 1 angles, sir. So
Okay.
in pre-controlled bridge configuration of RL load, we have considered theta greater than that of 90 degrees like that. And coming on to this RLE load, we have considered both theta and theta 1, sir. I just want a clarification that where we have to consider theta and where we have to consider theta 1.
Okay, I will tell you. Okay, just a minute. Yes, this is a RE load. Here also we are having a theta.
Yes, sir.
Okay, now you can check. First we discuss RE load. After that we will discuss RLE load. Okay, so that you will understand. Okay.
Yes.
So you can check here. What is happening here at theta? VS and E both are same.
Yes, sir.
At pi minus theta also VS and E both are same.
Yes, sir.
Now in RLE load, if you check in RLE load, we are having a concept like theta 1. Na? Just a minute, let me show RLE. Yes, here it is RLE load. I have added here theta 1. Na?
Yes, sir. Yes.
So here you can check theta and pi minus theta. These are same as that of your RE load only. Yes or no?
Sir, I didn't get it, sir.
This theta value and pi minus theta.
Yes, yes.
Is the same as that of your RE load only.
Yes, sir.
Okay, this should be theta actually, right? We have written here theta, so this should be pi minus theta. Okay, so it is similar to that of your RE load. This is pi minus theta, na? This is not pi. This is pi minus theta, and here it is theta 1. Where I have written, na?
That's
So
what.
what is the thing? You can check here. In a RLE load, this theta 1 means what? It is the instant till which inductor stores energy. Means you can check at omega t is equal to theta 1. It is like a inductor voltage becomes 0.
Okay, sir.
Means from alpha to theta 1, inductor stores energy.
Energy. Okay,
At
sir.
theta 1, because you can check in a network transient also, as soon as at the instant of switching, if initially inductor current is 0, at the instant of switching, inductor acts as open circuit, na?
Yes, sir.
So if inductor acts as open circuit at the instant of switching, means voltage across inductor is high.
Yes, it is high, sir.
Yes. So at pi minus at theta 1, what is happening? So from this alpha till this theta 1, it is like our inductor is storing the energy.
Okay, sir.
At theta 1, inductor voltage becomes 0. Means at alpha, inductor voltage is high. From alpha till as we reaches towards the theta 1, na, inductor voltage go on decreasing. At theta 1, inductor voltage becomes 0.
Okay, sir.
Right? Same concept in the network you can check. At the instant of switching, inductor acts as an open circuit. At the steady state, inductor acts as short circuit, na? Short
Yes.
circuit means 0 voltage.
0 voltage.
So from alpha to theta 1, inductor is storing the energy. After theta 1, inductor releases the energy.
Okay, sir.
Are you getting the point? Means this theta corresponding to theta 1, what is the value of Vs we are having, na? This Vs is nothing but your E plus VR.
Okay,
You can
sir.
check. You can check when T1, T2 are in a conduction mode, na? It is like Vs, T1 load, T2, and again back to the Vs. In this loop, current will flow, na?
Yes, sir.
So can I write Vs is equal to VR plus VL plus E?
Okay, sir.
Please listen. Vs minus VR minus VL minus E na, is equal to 0.
Yes, sir.
So therefore, can I write Vs is equal to VR plus VL plus E? Yes.
Okay, sir.
Now in this case, you can check Vs is equal to VR plus VL plus E. So what is VL? VL is equal to Vs minus VR minus E na?
Yes, sir.
So as at theta 1, I am saying VL is 0 means what? Vs is equal to VR plus E na? Then and only then your difference Vs minus VR minus E becomes 0 na?
0. Yes.
The meaning is at this instant it is become 0, and you can check at pi minus theta we are having Vs and E both are same.
Yes.
At this instant we are having both are same na, Vs and E. But
See,
if I add VR na, then therefore your Vs should be somewhat greater than that of this point na.
Yes, sir. It's magnitude.
That's why I have taken it as a theta 1, right?
Okay,
it is
sir.
just before to pi minus theta.
It is the theta 1 is the point where we have added R value to the Vs.
Theta 1 is the point where Vs is equal to VR plus E. That is nothing but your VL is 0. Please note it. Theta 1 is the point where VL is 0. VL 0 means what? Vs is equal to VR plus E na?
Okay, sir.
Right? So that's why VL is 0. Means till this instant, your inductor is storing the energy. After this instant, inductor will release the energy.
Okay, sir. Okay.
Right? Okay.
Okay, sir.
This is
Thank
for REL E load. And for REL load, we don't have concept like E na?
Yes, sir. No E.
So it is like this. Just now. Yes, just a minute. Yes, for REL E load. Yes, this type of thing we are having. REL load, REL not REL load.
Yes,
This
sir.
type of thing we are having. REL load means current is like this now we are having.
Yes, sir.
And we generally discuss till theta it increases, after that it decreases. Means in REL load what is happening? At theta VL is 0. At theta VL is 0.
Okay, sir.
So if VL is 0, meaning is your Vs is equal to VR na?
Yes,
So
sir.
you can
Yes.
check Vs waveform is this one, blue one, and this black one is your VR waveform na?
Vs is
At
equals
this
to.
instant what is happening? VR and Vs both are same.
Yes, sir.
So that's why that instant is theta, right?
Okay, sir.
Please
Okay,
keep it in mind that theta or theta 1 corresponding to that instant your VL is 0. Okay?
okay, sir.
Right. Okay.
Thank you, sir. Thank you.
Okay. Right. Okay. Okay, so we'll stop here. Tomorrow we'll be meeting at same time. Okay. Money Vandans, why we need to trigger after 90 degree? Because we are interested in inverter mode na. So that's why alpha should be greater than 90 degree only. Then only then your V0 will be positive. right? Why reverse voltage is appearing, Pawan Kore? Because inductor releases the energy, na? So that's why your voltage is negative, right? Okay.
Hello, sir.
Yes, please.
Sir, actually, I asked one question about peak inverse voltage of single, suppose L load. Sir, in that case, sir, I send a question on the WhatsApp to you. Sir, in that case, I did not get the what is the peak inverse voltage in the case of L load when the firing is less than 90, sir.
No.
I
Generally,
sent,
yes. Generally, the thing is,
yes.
PIV, it is a rating.
Okay.
Okay.
Yes,
Suppose
sir.
I am a
Yes.
manufacturer.
Yes, sir.
Suppose I am manufacturing the SCR.
Yes, yes.
I
sir.
don't know where that SCR is going to use in which circuitry. I don't know. I
Okay,
don't
sir.
know which for which alpha they are going to operate. The user is going to operate that SCR. We don't know, na?
Okay, okay.
So
But sir, suppose
generally,
yes,
the
yes, sir.
PIV rating is specified in general way. It is independent of
okay.
alpha. Your alpha, anything, alpha will be anything. But your
Okay,
PIV, okay, should be
Yes, sir.
same only. That will be only one value. It should not
Okay.
be in the
But
form of your alpha. Okay.
okay. But sir, suppose question is like that they given a firing angle less than 90 degree, and in that case they told us or they asked us that we have to find the peak inverse voltage, sir. In that case, sir,
Then it is a Vmax.
how,
If
sir,
alpha is
means
less than 90 degree,
yes.
which circuitry they have given?
Suppose L load, we use even
Okay.
L load,
Then for L
and
load, yes. We need to draw
yes,
the
sir.
actually waveform and this.
Yes, yes,
For
sir.
L load,
Yes,
let me draw here. Omega t 0. If alpha is
yes,
less than 90, na?
yes,
I'm
sir.
drawing the VT waveform directly. Yeah.
Yes, yes. Okay, sir. No problem.
Alpha, here it is like pi by 2, na? Here
Yes,
it is
sir.
a pi.
Pi
Yes, it is
and
like pi plus alpha.
yes,
And here it is 2
and
pi,
just
na?
2 pi. Yes, sir.
So you can check here. In L load, we discussed
Yes,
suppose
sir.
alpha is less than 90 degree means from alpha till pi,
Yes,
inductor stores energy.
yes, sir.
After that, inductor will take same time to release the energy.
Yes, sir.
So it will be like this from at this point till from this point till the from alpha till this point,
Yes,
na?
2 pi minus alpha.
Yes, this
Yes, sir.
point is very good. This point is like 2 pi minus alpha.
Yes, sir.
Till this instant, our inductor will be in a conduction mode.
Yes,
Right?
sir.
Inductor, not
Yes.
thyristor.
Sorry, thyristor.
So
Yes,
after that, it will be in a reverse bias mode.
sir. Yes, sir.
So voltage across thyristor will be like this. Here it is negative and this type of thing.
Yes, sir. In that case, sir, I am
So
asking.
whether they have given alpha value,
Yes, sir. They given alpha value, and
then no
that
issue. Then we need to find this value actually.
okay means, sir, it will be less than Vm, na, sir.
Vm into, yes, it will be less than Vm, definitely.
Okay, and sir, same condition will be happen in any type of load like RLE load or RL load we using. In that case, sir, suppose alpha is greater than 90 degree. In that case also, sir, same condition will happen. Na?
Yes.
In that case, yes.
Same. Means we need to
Okay.
we need to go through the circuit operation, and accordingly it
Okay.
will vary. It will depend. Okay.
Okay, means, sir, we can generalize like that in the case RLE load or this type of load, when alpha is or firing angle is greater than 90 degree, then peak inverse voltage is Vm sin alpha, and in L load, when firing angle is less than 90 degree, in that case peak inverse voltage is Vm sin alpha. We can generalize in that way, sir.
Suppose my question is, we are having a
Okay.
purely resistive load,
Yes, sir.
and I am keeping alpha greater than 90 degree.
Yes, sir. No,
Or
sir.
any value of alpha.
Yes.
It doesn't matter, any value of alpha. For purely resistive load, what is the PIV
Okay.
rating? By
Yes,
default,
sir.
it is a Vmax.
Definitely. Yes, sir. Vm, sir.
Okay.
V maximum.
Means whatever you are saying, it varies actually circuit to circuit and load to load.
Okay, sir. It will be applicable only for RL load and RLE load, na, sir.
Yes. For RLE, that will be okay, right?
Alpha is greater than 90.
Yes. Okay.
And inductive load alpha is less than 90. Okay, sir.
Yes, correct.
Yes,
Okay.
sir. Thank you so much, sir. Got
Okay.
it now.
Yes.
Yeah.
Okay.
Yeah. Thank you.
Right. Okay. So thanks to all of you. Tomorrow we'll be meeting and tomorrow we'll be discussing about single phase half
Okay,
controlled
yes, sir.
bridge rectifiers, right? And we'll
Yes,
discuss
yes,
some
sir.
numericals, and after that very important concept, that is the input power factor. Don't miss it, very interesting. We are going to introduce the Fourier series analysis tomorrow. Okay, right?
Okay,
Full
okay,
of mathematics.
sir.
The subject is full
Yeah.
of mathematics, but it is interesting, right? Okay.
Okay. Thank you so much, sir. Good night, sir.